In the previous chapter, we made the distinction between elements and compounds when discussing types of pure substances. In this chapter, we're going to talk a little bit more about what it means to be an element. What is an element? What are these atoms that make up our molecules and make up just make up matter in general? These smallest building blocks of matter. And I think to understand how these atoms work and how they make elements to begin with, you kind of have to dive a little bit deeper. Even though atoms are the smallest working units we have in chemistry, it's possible to break them into even smaller pieces. And by understanding those smaller subatomic particles, we can figure out what makes atoms of different elements different. So, first of all, let's ask ourselves, what do we mean by an element? So, elements are a way of distinguishing different types of atoms. All right, so if you have an atom of one element, it's just going to be different from an atom of another element. Okay, we'll understand how they're different in a little bit throughout this chapter, but for now, understand that elements are the ways we sort of classify different types of atoms. Now, we can break this down into almost 120 elements. If you look at your periodic table, there's a square devoted to each one of these elements. And theoretically, you could keep on expanding the periodic table as long as you have enough energy. You could keep on building bigger and bigger atoms, essentially. But the bottom line is that most of these are found in nature, but about 100 of them or so, though only about 80 or so are stable. In the next chapter, we'll get into some nuclear chemistry and understand how these unstable elements kind of decay or undergo, nuclear reactions. But basically, with some of the other elements, which are also radioactive, those are man-made, we could make them in a lab, they tend to be very short-lived. Okay, so they tend to decay really quickly. They don't last a very long time. To be honest with you, in this class, they're not very important. You're only going to probably come across, say, roughly about 20 to 30 elements that you'll use on a regular basis. So, get comfortable with those ones and don't stress too much about some of the heavier elements, just because we're not going to do a lot of chemistry with those. Okay? So, what does it mean to be an element? Again, in the last chapter, we talked about how pure substances could be broken down to elements or compounds, right? And if you have a sample of an element, it means that all of the atoms making up that sample are identical in a certain respect. So, for example, over here, we have a sample of charcoal, which is pure carbon. Okay, now carbon is an element you'll find in your periodic table. Okay, it's the element with the letter C, element number 6, and it basically, by knowing that this is, charcoal, it means each of the atoms making up the sample are carbon atoms, and all of those atoms are identical in that respect. Okay, now it's possible to, of course, have compounds. This is the other type of pure substance we discussed in the last chapter. So, for example, water is a compound made up of two different elements. We have our water molecules that have two hydrogen atoms bonded to an oxygen atom. So even though our water molecule is H2O, within that water molecule we have two individual hydrogen atoms and one individual oxygen atom making that molecule. And oxygen and hydrogen are separate elements. Likewise for carbon dioxide. We have carbon and oxygen making up carbon dioxide, and carbon and oxygen are two different elements. Okay, we'll talk about this naming convention, how we get that name carbon dioxide, in a later chapter. Okay, we'll talk about where compounds come from or how do we build up compounds later on. For now, let's understand elements and how they make those compounds. How do we treat those individual elements? So, you've probably noticed that we use certain symbols to represent the elements. Every chemical element has a 1 or 2 letter symbol. All right. In some rare cases, when an element doesn't have a name yet, you might have 3 letters to represent it. If you have an older periodic table and you look down to the towards the bottom right, you may have certain elements listed with three letters. For example, the old name for element 118 was unum octium, which is 118 in Latin. Of course, it's now got an actual name, but and it's got a two-letter symbol representing that name. But until they did that, its working name was unum octium, and its symbol was UUO. So that's one of the rare cases where you happen to have three letters representing a chemical, which, again, don't worry about that for this class. You're not going to deal with any of those new elements. So for the most part, most of your elements have one or two letter abbreviations representing the element that's in question. Now, that first letter is always a capital letter. This is important for when we do start writing out compounds. Every time you see a capital letter in your formula for your compound, you know that that capital letter references an individual element. All right. So the second letter is always lowercase. So if you ever see a capital letter, an uppercase letter, and a lowercase letter, you know that they are combined into one element symbol. Okay. Now, in the case of knowing what symbols correspond to which elements, in some cases it is kind of straightforward. For example, fluorine has a symbol F. All right, phosphorus has a symbol P. Sulfur has a symbol S. Oxygen has a symbol O. These are relatively straightforward. The first letter represents the first letter of the name represents the symbol that we use for that element. Though your quick counters amongst you probably figured out, okay, we're going to have like 26 of those, and then we've got to stop, right? There's only 26 elements where we can just use the capital letter. And you then might say, like, okay, we have a lot of combinations after that. However, some of you might notice that sometimes the symbol doesn't seem to match up with the name of the element. For example, lead symbol is Pb, right? Or sodium is Na, or gold is Au, right? Where do these names and symbols, how are they connected? In the case of some of these older metals, the names are derived from their names in Latin. So, for example, lead, which the Romans used for plumbing, was named plumbum, and so the symbol Pb comes from that Latin name. Okay, so gold is Au because aurum means shiny metal in Latin, which obviously gold was. And so on. So if you look at any of those symbols that don't seem to correspond to the names in English, it's because they correspond to the name in a different language. Usually Latin, in a few cases, sometimes other languages. Tungsten is W from the German wolframite, for example. Anywho, I could probably go on this because it is kind of neat sometimes looking at the roots of some of these names, but and if you're bored, I really recommend looking them up. It's kind of interesting extra reading, but let's move on. Okay, so you're probably asking from a practical standpoint, okay, that's great, they're names and symbols, whatever, what do I actually need to know? Again, you do not need to memorize your periodic table, right? You have, on a quiz or exam, you'll be given a periodic table, or if we're working remotely, you are allowed to have your own periodic table while you're taking a quiz. So I don't expect you to memorize your periodic table. That'd be silly and a waste of effort. What I do need you to do is to be able to connect symbols and names yourself. On a quiz or exam, typically when we're meeting in person, the periodic table that's usually provided to you doesn't have names on it. It's usually just the chemical symbols. So you would be expected to know the names that correspond to the symbols in your periodic table. Now, that being said, we don't use all of the elements in your periodic table, so you do not need to memorize all the names in your periodic table either. You want to know some of the more common names that you might come across. So in your textbook, there should be a table that lists out some of the more commonly used chemical elements that you just tend to use on a regular basis in a class like this. So do get comfortable with those names. Again, I don't expect you to necessarily get that right off the bat. This is something that takes a little time. So in the next few quizzes and exams, I'll probably give you both the names and symbols. But my hope is that towards the end of this semester, you'll start not needing to be told what the names and symbols are. You'll just start to be able to pick it up by yourself. So what I recommend is perhaps having that table in front of you when you're doing your homework, and refer to it whenever you need to. But my wish for you is that eventually you will have to refer to it less and less, and eventually not at all. All right, so I've referenced the periodic table a few times. What exactly is a periodic table? The periodic table is a way to organize the elements. It makes looking up individual elements and noticing patterns in their properties a lot easier. All right. Dmitry Mendeleev was a Russian scientist who first organized the periodic table. Legend has it that he loved playing a card game called Solitaire. And if you've ever played Solitaire, you know that you've got to arrange your cards in rows based on value. So the rows are by suit, and you arrange and you just like number your cards, ace through king. But basically, what Mendeleev noticed was that when you organize the elements in a certain by certain properties. So he used atomic weight or atomic mass. So as the elements got heavier, he noticed that these properties tended to repeat. There was a repeating pattern in the elements. Okay, and so essentially every time he got so as he was like listing out the elements in order of mass, every time he got to an element that had a similar property, he then put it in a new row under a similar element. Okay, and then he continued on, and he noticed that he kept on having this repeating pattern of every like 7 elements or so, because back then the noble gases hadn't been discovered yet. Okay, and that's why the periodic table is called the periodic table. The properties of the elements repeat periodically, hence the name. Now, one little change that we have from Mendeleev is instead of organizing the elements by mass, we use what's called the atomic number. So if you look at your periodic table, you will notice that all of your elements are organized going from left to right and top to bottom in order of this atomic number. So looking at hydrogen in the top left corner, that's element H, you'll see the number 1 written in that box. And to its right, all the way at the right of your periodic table, is helium, element He, and that has atomic number 2. And then on the next line, you'll see lithium, symbol Li, with atomic number 3. And so on. As you keep on going from left to right, you will notice that those numbers keep on increasing, and they are in sequential order. Okay, so we call these rows where we have these repeating patterns periods. Each of these horizontal rows are known as periods. And the columns, where all the elements in a given column have similar chemical properties, those columns are called groups. Okay, they're sometimes called families. You may hear that term, but I think groups is probably the more common name given to these columns. All right, so the columns then are numbered accordingly, and the basically, depending on how old your periodic table is, you might have different headings for your columns. Nowadays, modern periodic tables tend to number them just 1 through 18, keeping it relatively simple. There are 18 columns, and they just number them really straightforwardly. But if you get older periodic tables, they tend to distinguish between what are called main group elements and the transition elements, the sort of bridge that connects your periodic table. All right. So if you're having trouble seeing that, basically you could divide your periodic table into a kind of block. So, or into a four rather block. So if you looked at your periodic table and I were to just sketch it, it would look something like this. Okay, so if I were to make a rough schematic of our periodic table, it would look something like this. Okay, I mean, obviously you've got like, hydrogen and helium over here, as like sort of on top of that block there. Um, if we were to label these four blocks, this would be the S block, the P block, the D block, and the F block. Okay? Now, what those letters stand for, you'll see later on in this chapter. You'll realize there is a reference to those blocks later on. But for now, those first two columns are called the S block. The 6 columns all the way on the right are called the P block. The 10 columns in the middle are the D block. And the F block is 14 columns. Okay, it's just 2 rows. It's very short. If you look at the atomic numbers making up your F block, you'll notice that your F block actually gets inserted over here between the S and the D block. You'll notice the way the numbers are lined up. They tend to do that. The reason for this is that your periodic table is supposed to look like this. So here we have an S, P, D, and F. The problem with drawing your periodic table like this is very wide and narrow. It does not fit very well on a page. So most people just take out the F block and move it to the bottom like you see in your typical periodic table. Okay, so that's why you might notice that jump in numbers from these elements down here and these elements over here in the D block. It's because the F block represents those numbers there. Okay, so what do I mean by main group elements? So your first 2 columns and your last 6 columns, what are labeled 1A through 8A, are the main group elements. Okay, the modern periodic tables have those first 2 columns as 1 and 2, and those last 6 columns as 13 through 18. Okay, and of course the middle, those transition elements in the middle, in that sort of bridge in the D block and F block, those are sometimes labeled with a B in the old periodic tables. Okay, so why are we making a distinction between main group elements and transition elements? The reason for this is those main group elements, the ones in the S and the P block, as the name suggests, are very mainstream. They're very normal. They're easy to predict. Their properties are generally easy to follow. So that's why they tend to be called main group or representative elements. All right. In a later chapter, when we start looking at ionic compounds, we'll see that they are very easy to figure out in terms of what types of ions do they form, what types of ionic compounds. So don't stress about that for now. We'll get into that in a later chapter. But you'll see that the main group elements are really straightforward in that respect. The transition metals, on the other hand, are a little bit different. Their difference in properties aren't very noticeable, so they tend to all have very similar properties. They mark a transition from the S to the P block elements. So, they're kind of, so I guess that's kind of where the name comes from. But basically, one of the key things that's interesting about them is that they're ions can have multiple charges. They can form different kinds of ions. And this yields a lot of really interesting chemistry about them. Okay, in fact, that's kind of the bulk of what inorganic chemistry is. To give you an example, iron, okay, symbol Fe from the Latin ferrum, can come in 2 varieties. It could either have a 2+ charge or a 3+ charge. Okay, and this again leads to very interesting chemistry with iron. The reason you're able to breathe right now is because iron can do this. The hemoglobin in your blood has iron at the center of it, or an iron ion. When it's regular hemoglobin, it's in this 2+ state. When it picks up oxygen, it moves to this 3+ state. So basically, its ability to absorb oxygen from the air is because iron can do this. Okay. Anyway, so main group elements can't do this. If you had a sodium ion, sodium ions always have a +1 charge. You're not going to find a sodium ion that doesn't have a +1 charge. whereas like transition metals like iron, for example, can do that. Okay, and so that's one of the cool things about the transition elements. Quick note here about the lanthanides and actinides. I'll point these out in your periodic table in a slide or two. But these are named after the elements at the start of your F block. So the lanthanides are the elements that follow lanthanum, symbol La. Okay, so if you look down at your F block on your periodic table, you should see that, that symbol La. So the lanthanides are the elements that follow that. And then the actinides follow actinium, symbol Ac, also in that second row of your F block. Okay, so like the lanthanides and actinides, a lot of groups have special names to help you refer to them sort of quickly or as a group. Okay, so the metals in group 1 are known as alkali metals. Okay, so this is with the exclusion of hydrogen, even though hydrogen is technically sort of in group 1. Okay, some periodic tables have hydrogen as a little island by itself because of this. But anyway, the group 1 metals are known as the alkali metals. Group 2 are known as the alkaline earth metals. Okay, the group 8 are the noble gases. Group 7 are the halogens. Let me show you those on your periodic table. Okay, so here, so this periodic table accidentally lumped in hydrogen with the alkali metals, but usually you'll find it as sort of an island by itself. So your alkali metals are this first column over here. Okay, they're known as that because they tend to form alkalis or really strong bases when they dissolve in water. And they have other very similar properties. They all tend to react violently with water. They all tend to be reactive in general. You know, they all form +1 ions, you know, things like that. The alkali metals, the alkaline earth metals are the group 2 elements. They're kind of like the alkali metals, but maybe turned down a notch. So they're reactive, but not as reactive as the alkali metals, for example. Okay. Over here we have group 18. Those are the noble gases I pointed out earlier. So that includes helium, all the way down to radon. Okay. So the noble gases are they're called noble because they don't like to bond with things. They tend to just stay by themselves. Right? They tend to just stay in there as atoms. They don't like to form compounds. They're all gases at room temperature for similar reasons. And yeah, basically, including, so when I say they don't like to combine with other elements, it's really they don't like to combine with other atoms, including atoms of, you know, of their own. So they tend to stay in that gas form because they don't like coming together as a liquid or a solid. Over here in group 17 or 7a, if you've got an older periodic table like I have up here, those are the halogens. They are, unlike the noble gases, these nonmetals are very reactive. Okay, they tend to be very reactive. They tend to be brightly colored. You know, there are other names for certain other groups. So, for example, oxygen and sulfur are considered part of the chalcogens and so on. I think nitrogen and phosphorus are the pterogens. You really don't need to know that. I'm just giving you random trivia. But in case you're curious, there are names for other things. And again, they're very useful for referring to these things as a group. So if you were talking about a group 1 metal in general, you could just call it an alkali metal. You don't have to say the individual name of all of the alkali metals. All right. Here we have the lanthanides and actinides. So you can see here I was talking about that jump from the S block to the P block, between the S block and the D block. Notice we have a jump here from element 57 to 72. Okay. Oops. That's because this F block is actually supposed to be inserted in here. So these elements here in green follow lanthanum, element La, and these elements here in kind of a dull red follow actinium. That's why they're the actinides. Okay, different periodic tables draw the F block a little bit differently. This one kind of includes lanthanum and actinium in the D block. Sometimes periodic tables tend to put lanthanum and actinium down here in your F block, and they would put these two elements, lutetium and lawrencium, over here instead. It depends on your individual periodic table. it's not important. Don't stress about it for this class for sure. It's just a different way of noting those elements is all. Okay, but you'll still notice that there's still that all the elements are still in numerical order. So you go from, element number 55, 56, 57, and then 58 all the way through 71, and then you pick up with 72 onwards here. Okay. Likewise with elements 87, 88, 89, and then 90, 91, and so on, all the way to 102, 103, and you pick up with 104, 105, and so on. Okay. This is a pretty old periodic table. There are more elements all the way here, going all the way up to Unum Octium, which would have been over here. They aren't filled out at all. And here you can see some of those 3-lettered codes I was talking about. All of these elements over here now have 2-letter symbols because they have been named elements. But this periodic table is an older one and doesn't list them. Okay? All right. So again, I recommend getting comfortable with some of those names just so that you can quickly look up where these elements are located. Okay. I'll also draw your attention to the numbering of the groups. So notice that here I've used this is an older periodic table and it uses the A designation. Okay, so this is group 1A, 2A, 3A, and so on, right? But if you have a newer periodic table, you'll just notice these numbered 1, 2, 3, 4, 5, so on, all the way up to 13, 14, 15, 16, 17, 18. All right. So be comfortable either way, just seeing those. Also, I'll draw your attention to the periods. Notice that hydrogen and helium are the only elements in that first period, that first row. In the second row, in the second period, we have lithium and beryllium, and then a jump over to boron, carbon, and so on until neon. Notice that the D block only begins in the fourth period. Okay, so it's only in the fourth period that we start getting elements in that bridge, the D block. We'll discuss why this happens later on in this chapter. Okay, so I just wanted to point out that this is kind of where, how your periodic table is broken down. So just once again, remember that, if we were to divide these into blocks, right? That's your S block. This is your P block. This is your D block. And of course, this F block would be inserted in here. Okay? So something to keep in mind. The other thing I want to draw your attention to, okay, over here, is the, let me erase this for a second. The other thing I want to draw your attention to is this sort of staircase border that we have in our periodic table. It kind of serves as the border between metals and non-metals in our periodic table. Things to the left of this border, including the lanthanides and actinides, because they're inserted over here, are what we call metals, okay, which, if you ever forget, the fact that these are called alkali metals, alkaline earth metals, transition metals, that should kind of give that away, that the metals are towards the left of that border. Things to the right of the border, so in the top right corner of your periodic table, these are non-metals. Now, what do I mean by metals versus non-metals? Well, they're grouped together because they have similar properties, metallic properties and non-metallic properties. Metals tend to be shiny, they tend to have higher melting and boiling points, they tend to be really good conductors of heat and electricity, and they tend to be very easy to shape. They're what we call ductile or malleable. Malleable means that you can hammer them into shapes, including like thin sheets. Ductile means you can draw them into wires very easily. All right, that's what that means, that you can shape metals really easily. If you hit them with a hammer, they'll form nice sheets. They won't shatter due to that force of that hammer. So they're malleable. They're not brittle. Okay, they have good tensile strength, I guess is another term you might hear for them. Okay, they're kind of strong in that respect. Non-metals, on the other hand, tend to have, not be shiny. They tend to be dull. They tend to be poor conductors of electricity, what are called insulators. They tend to have lower melting and boiling points. You'll notice that not too many of these are solids. A lot of them are liquids or gases at room temperature. Okay. Now, of course, there are exceptions to some of these things. Like diamond is made from carbon, which is, obviously a really hard material, has a very high melting point. That's like, one of those exceptions. All right. But the majority of nonmetals tend to have very non-metallic properties. Okay, so we're distinguishing between metals and nonmetals, but what about the elements that are on that border? So if we go back to this periodic table, what about these elements that are sort of touching that staircase? So aluminium over here, Al, is a metal, so I'm going to skip that, but boron, so skip aluminium, silicon, germanium, arsenic, antimony, tellurium, and then kind of polonium and astatine as well. So if we look at those elements, okay, so looking at, all the things touching the flat parts of that staircase, right? So boron, again, I'm going to skip aluminium. And by the way, I say aluminium because I'm foreign, and that's like the way you spell it. And most people spell aluminium like this. I think Americans tend to leave out the second I, and that's why the American pronunciation is aluminum. If you pronounce it aluminum, I'm not going to take off points for that. That's totally fine. Okay, just in case you're wondering why I pronounce it a little bit differently. Anyway, so boron, skip aluminium, we've got silicon, germanium, arsenic, antimony, tellurium. Polonium and astatine you'd think would be included in this. It's whether or not they are is kind of up for debate. Polonium, some people classify it as one of these metalloids. Some people classify it as a metal. So some people, it's kind of up for debate whether or not we'd include it with this group of metalloids. To be honest with you, it's also kind of radioactive, so it probably doesn't stay polonium very long, so it's kind of hard to tell. Astatine is one of the rarest elements in the world. Like, no one really knows anything about it because it's so rare that there's not enough of it to study. So whether astatine's more of a halogen or more of a metalloid, no one knows. So I'm going to skip these two. For now, these are the main metalloids, the ones I've circled here that you're going to see. Now, what do I mean by a metalloid? Well, a metalloid, as the name suggests, has properties that are kind of in between those of metals and nonmetals. All right. Now, out of all these properties, probably the most interesting one, the most practical for metalloids, is their ability to be semiconductors. So remember, metals are really good conductors of electricity. Nonmetals are insulators. They don't conduct electricity. So metalloids are kind of in between. They conduct electricity, but only kind of semi-effectively. They're not as good conductors as metals are, but they still conduct electricity. Okay, so this yields some very interesting applications, most notably in computer chips. That's why a lot of computer chips use, I think the biggest use of silicon is for making computer chips. All right, and just general, just semiconductor boards in general. Okay, and usually you can use small amounts of the other metalloids as what we call dopants. You use tiny amounts of them to change the conductivity properties of your semiconductor. Okay, so like I said, these ones are the main metalloids you need to recognize as being metalloids. But again, if you have a periodic table, just remember they're the ones touching the flat parts of that staircase border. Okay, though of course skip aluminium. Aluminium is strictly a metal. Okay, so with types of elements squared away, let's talk about atoms themselves. I've mentioned that atoms are the building blocks of matter. When we look at, if we were to break things down, break down just matter into smaller and smaller pieces, the smallest working unit that we use in chemistry, the smallest practical unit, is the atom. Okay? So when we're looking at things as being pure substances, we're essentially looking at the types of atoms we're dealing with. But what are atoms, right? So John Dalton was an English school teacher and scientist who lived around, the early 1800s, so around the turn of the 19th century. And based on his experiments and just his deductive reasoning, he kind of summarized 5 rules or 5 statements about what it meant to be an atom. What are atoms, according to John Dalton? And this is known as Dalton's atomic theory. Now, what's really neat about this is obviously he didn't have a lot of sophisticated equipment, but he was surprisingly accurate. He was kind of spot on with most of his deductions. We still hold Dalton's atomic theory as being valid. Like, we still use it to understand atoms or to describe atoms even in our modern setting. Okay, there's one small exception, which I'll point out, where he was slightly wrong, but that was also because his work predated anyone understanding nuclear chemistry. All right, so what is Dalton's atomic theory? What are those 5 statements? One, all matter is made up of atoms. So atoms are these small particles that you can divide matter into. Okay. Now, this, by the way, wasn't a new concept. The idea of being able to divide matter into smaller and smaller pieces and eventually getting to a piece so small that you can't divide it any further, that idea had been around since the ancient Greeks. That's actually where the word atom comes from. It's a Greek word meaning indivisible. All right, and I think it was a Greek philosopher Democritus who kind of posited that. So that's been around since ancient times. But Dalton basically said, okay, based on all the evidence we've got right now, we can kind of scientifically show this. Okay, all matter is made of these small particles called atoms with different types. So the atoms of a given type that are similar to each other are one type of element, and if they are going to be different from other elements. So essentially, you can divide all these atoms into elements, and that's what distinguishes one atom from another. Atoms that are similar to each other are one type of element. If they are different, they are a different element. The number and arrangement of different types of atoms help identify a pure substance. So now we're getting into compounds, right? So if different atoms in an element, are the same, okay, and if you have different elements, the atoms are different. The same could be said for compounds. When you combine atoms in different fashions, you make new elements. Okay, so if you take carbon, you make new compounds, but new substances. So if you take carbon, which is an element, you take oxygen, which is an element, you can make carbon dioxide, which is a compound, which is different from both carbon and oxygen, right? You can take hydrogen, which is an element, oxygen, which is an element, and you can make water, which is going to be different from hydrogen and oxygen. Moreover, you can combine these in different amounts. So instead of taking 2 hydrogens and 1 oxygen to make water, you could take 2 hydrogens and 2 oxygens to make hydrogen peroxide, which is going to be completely different from water. Instead of using 1 carbon and 2 oxygens to make carbon dioxide, you could use 1 carbon and 1 oxygen to make carbon monoxide, which is going to be different from carbon dioxide. Okay, so my point here that Dalton's trying to make is that number and arrangement of those atoms in compounds will change their identity. So compounds can be different if you use different elements to make them up. Okay? Chemical reactions, as we know them, chemical changes, are just simply the separation and rearrangement of these atoms. Basically, when you do a chemical reaction, you can break apart the bonds holding them together in a molecule. You reshuffle and rearrange the atoms, and you form new bonds. And now, because you've made new combinations of elements, you've made new chemicals. That's what a chemical reaction is. Okay? And then finally, only whole atoms can take part in these types of reactions. And I've worded it here to kind of reflect Dalton's understanding of it. So basically, we say that only whole atoms take part or result from chemical reactions. Basically, you can't break apart atoms. They only, they stay intact. Uh, Again, this was only kind of disproved, or rather had to be rethought of, or redefined, kind of in the early to mid 20th century, when we started learning more about nuclear chemistry. And we'll talk about that in the next chapter. But you'll find out in the next chapter, we can now do reactions where you can, basically break apart atoms, okay, and you can then change the identity of those elements accordingly. Okay, this was previously thought to be impossible, right? It was one of those things that a lot of pseudoscience like alchemy used to try to go for, but Dalton and scientists of his day quickly showed that, like, no, alchemy is pseudoscience. You can't actually do this. You can't change one element into another. So anyway, that was Dalton's atomic theory. All right, so just to summarize, basically, atoms are indivisible. You can't break them down into smaller pieces, according to Dalton. We'll talk a little bit about how that idea changed a little bit in years in the future. But basically, when it comes to chemical reactions, atoms stay whole, and they take part in these chemical reactions. They get rearranged. Okay, but atoms of one element cannot be changed into atoms of another element through a chemical reaction, at least. Okay, so for example, one of the holy grails of alchemy was to try and turn lead into gold using what was called a philosopher's stone. But basically, that's you can't do that using a chemical reaction like alchemy implied that you could. We know now that you can do it through a nuclear reaction. It involves a lot of energy and it's kind of difficult, but it is possible. But you can't do it with a chemical reaction. So, that being said, how do different elements come about? I pointed out earlier that in order to understand what makes an atom of an element, like that element, we have to kind of break atoms apart into smaller pieces and study those pieces to figure out where elements arise. What makes different atoms different? It's these smaller pieces that do it. The numbers of these smaller pieces, these subatomic particles. So again, in Dalton's time, he thought that you couldn't break down atoms any further. And again, this was an idea going back all the way to the ancient Greeks. It was about a century, almost a century after Dalton, right, towards the end of the 1800s, so the end of the 19th century, that people started doing some experiments that implied otherwise. That implied that, hey, perhaps we can break apart atoms, and maybe we should in order to study them a little bit better. So the first of these discoveries was the discovery of the electron. Now, this came about through studying what are called cathode ray tubes. And I've got a picture of a cathode ray tube here on this slide. So in a cathode ray tube, we have a glass tube, and it has gas in it at a very low pressure. So it's nearly a vacuum. In fact, you'll sometimes hear these called vacuum tubes. They're technically not a pure vacuum. They have a very low pressure of gas. Okay? But what happens when in your tube you have two electrodes? What happens when you run electricity through those electrodes is a beam of light shoots across your cathode ray tube. Now, it's called a cathode ray because it seems to originate from the negative electrode, which is called the cathode, hence the name. All right? So the negative electrode is called a cathode. The positive electrode is called the anode, in case you were curious about those names. So the cathode ray is this beam that shows up when you run electricity through this tube. Okay? So people tried to figure out what exactly is this beam? What does it mean? Right? And people would do experiments on them. You can see here one of the experiments was holding a magnet to the beam. People could put a very light pinwheel inside these tubes, and they found that the beam would be able to push the pinwheel, cause it to spin. Things like that. Okay, there were these experiments that people ran with these cathode ray tubes, trying to understand what are these cathode rays. The first person to suggest a plausible explanation, though, that he was able to back up, was J.J. Thomson. Okay, please note that's Thomson spelled without a P. It's not a typo. That's actually how Thomson's spelled. So J.J. Thomson uh, basically suggested that, he kind of looked at the evidence from these experiments and said, all right, what does this tell us about these rays? Like, what is this made of? Okay. Well, he first deduced that they must have mass, right? If they're able to push these pinwheels, the things pushing, making up this beam must be particles, and these particles have to have a mass that's capable of pushing these pinwheels. However, based on his experiments, he determined that they were very, very light particles. They must be very, very small and very, very light. He determined that they are much lighter than even a hydrogen atom, okay, which is the simplest element we know of, the lightest element we know of. All right. The other thing he noticed was that these particles must be negatively charged. Based on the way they deflected in magnetic fields and using certain static charges, he was able to deflect the beam of light, and he noticed that it got attracted to a positive charge and got repelled from a negative charge. So essentially, he assigned a negative charge to these particles. So he called these tiny negatively charged particles electrons. That was the name he gave that. And this was the first of the subatomic particles that was discovered. So in other words, when we pass electricity through the few atoms of gas that are present in this this cathode ray tube, okay, basically you are flaking off electrons from those atoms, and they're getting attracted to the anode. Okay, so that's essentially what's happening in a cathode ray tube. Okay, so you're basically using electricity to flake off these tiny subatomic particles that are negatively charged. Now, based on this, Thomson then tried to figure out, what does an atom look like? Right? Because up until now, people just figured okay, atoms are these little spheres, these little blocks that just kind of stick together, right? No one had actually ever seen an atom, so they just assumed that it's something that works kind of like that. But Thomson essentially said, okay, well, what are these sort of spheres? What are these atoms themselves made of? What do they look like? Well, if we flake off these negatively charged electrons, okay, that have a very light mass, what does that tell us? Well, if they're negatively charged, that means the rest of the atom must be positively charged. And if they're very, very light, that means the rest of the atom must have, well, most of the mass of the atom. So basically, Thomson pictured the atom as being this positively charged mass that was spread out throughout the volume of the atom. So it would be spread out relatively thin. So it's not a very dense atom, okay? And these negative electrons are sort of dotted on the surface. The way people described it was what was called a plum pudding model. They kind of pictured it like a plum pudding, where the electrons were raisins dotting the plum pudding. Okay, so it looks kind of like this. This is kind of how Thomson pictured the atom based on his cathode ray tube experiments. All right, so we of course now need to do more tests to see, is this a good model of the atom? Can we learn a little bit more about the positive parts of this atom, of these atoms, right? Is this what an atom actually looks like? Can we find more evidence for this sort of positive spreading out of mass? And that's kind of what Ernest Rutherford tried to do. He basically took, so Ernest Rutherford was a Scottish and New Zealand scientist from he did his experiments in the early 1900s. He basically fired alpha particles. So they're these this form of radiation that are these positively charged particles that he fired at a sheet of gold foil. All right, so he figured, okay, gold has really large atoms, is relatively high density, and he hammered this sheet of gold really, really thinly. So it was like about a few atoms thick, okay? And he figured that going off of Rutherford's model, these alpha particles should be able to punch right through these really low density that sort of like really spread out mass of these atoms. Okay. So what he did was he set up a detector behind his gold foil, try and pick up how these alpha particles were reaching it. Okay, and he figured this would be evidence of Rutherford's model. What he noticed was not all the alpha particles were making it to that detector at the back. So what he did instead was he set up detectors all the way around it. And then what he noticed was that while the majority of particles did make it to the back, some were getting deflected off to the side. Some were even bouncing back. Okay? Now, again, if you have Thomson's model of the atom in mind, this is really, really weird. Okay? Because Thomson predicted that the mass of the atoms kind of spread out. So a fast-moving alpha particle should be able to punch through it, but it's still more or less solid, right? What this showed is that, basically, instead of the mass being spread out, the mass had to be concentrated, but only in small places. So, in other words, it looks kind of like this. Basically, your atoms are mostly empty space, with your electrons going through and reaching the detector unharmed on the other side. But wherever the the alpha particles reach the denser parts of the atom, they would either deflect off due to their similar charge, right? Because these dense pockets of mass also were positively charged, and they'd repel those positively charged alpha particles. Or in certain cases, they would bounce off. They would, because these pockets were so dense, the alpha particles couldn't go through them, or they basically would bounce backwards. And this was the really weird anomalous data that Rutherford picked up and realized, like, okay, I need to come up with a new model of the atom based on this. All right, and that's kind of essentially what he noted, that the mass had to be concentrated into these dense pockets in the middle, what he called a nucleus. All right, so unlike Thomson, who suggested that the positive charge is spread out, Rutherford said, my data shows that they must be concentrated in the center. Right? Legend has it that this kind of freaked out Rutherford because, again, this is a huge paradigm shift, right? Like your idea of what an atom looks like is completely different now. Legend has it he had trouble getting out of bed the next morning because he was worried, because of all the empty space in atoms, he was worried he was going to sink through the floor. I don't know if that's just a story or not, but anywho. Yeah, so essentially what we have in an atom, according to Rutherford now, is that we have this nucleus at the middle, which has almost all of the mass of the atom, and it's surrounded by mostly empty space that contains the electrons, kind of like a mist or cloud of these electrons. All right. Now, further work by Rutherford and then by other scientists like Chadwick and Millikan helped distinguish what the nucleus was made of. Because quick reasoning will tell you that the positive particles making up the nucleus, which Rutherford eventually called protons, couldn't be the only particles in the nucleus, because if you take these positive particles and cram them together into a nucleus, well, positive particles repel each other, right? Well, so your nucleus would explode, right? Because these particles want to get far apart from each other. So there must be something that spaces them out, but that is just as heavy and that's kind of attracting them through a force that is not electrostatic interaction. So it's kind of, so not quite gravity, but like what's called a nuclear strong force that holds them together. So these spacing out particles are called neutrons. I think I have them on a separate side. There we go. So neutrons are these neutral particles that kind of space out your protons. Okay, so just to, by the way, just to give you an idea of like how tightly packed in we're talking about, if you were to picture, take an atom, okay, and let's say you were to expand it to the size of a football stadium. Okay, so if you zoomed in on an atom and it was the size of a football stadium, the nucleus would be the size of a pea at center field. Okay, so let that metaphor sink in. All right, think about how large a football stadium is. Okay, that's the size of your atom. Your nucleus which contains all of your protons and neutrons, which contains almost all of the mass of your atom. Okay? And because remember, electrons weigh next to nothing. Okay? They're very, very light. Almost all of the mass of your atom is concentrated into that tiny, tiny space at the center of the atom. Okay, so again, this is what Rutherford's data kind of showed him, and this is again why he was kind of afraid to get out of bed. There's a lot of empty space in atoms, essentially. Okay, so yeah, so those are the three subatomic particles that all of these experiments kind of led us to. Okay, so again, you picture this atom. You've got this nucleus here at the center, made up of the protons and neutrons. Okay, and the neutrons are neutral particles that help space out the protons to avoid them repelling each other and causing the nucleus to explode. And of course, that extranuclear region has the electrons sort of spaced out, kind of like in like a cloud or mist around it. Okay, and again, this diagram is drawn wildly not to scale. Okay, again, this should be much, much, much smaller. I've just kind of zoomed in so you can kind of see it. All right, so history lesson aside, the three key things I want you to get out of this is that when you need to be able to distinguish between these three different subatomic particles. Okay, so that includes where they're located, how much they weigh, what their mass, what their charge is, and also just in terms of a history lesson, just briefly knowing who discovered them and like kind of the names of the experiments they used. To be honest with you, you're probably not going to ever get asked about neutrons, so you don't really need to know about Chadwick or Millikan. Most times people ask you about Thomson and Rutherford. They're sort of the bigger names in this story. But basically, the key things to remember are electrons are these really tiny particles, like really, really tiny, really, really light. So light that we're going to say they have almost no mass. We're going to kind of treat them as having no mass. They're negligible in mass. But the key thing is that they are negatively charged. An electron has a charge of -1. Okay, and as I pointed out, J.J. Thomson discovered them using cathode ray tubes. Protons have a mass of about 1 atomic mass unit. Okay, we'll talk about what those are later on. And they have a positive charge. A proton has a +1 charge. Okay, and Ernest Rutherford discovered them while discovering the nucleus using his gold foil experiment. And neutrons are neutral particles also inside the nucleus, like the protons. You'll find that protons and neutrons are sometimes collectively called nucleons. You don't need to know that word, but in case you ever hear it, that's what it is. Yeah, so they also weigh about 1 atomic mass unit, and unlike protons, they are neutral. They have no charge. Okay, so that's kind of the key takeaway in terms of the difference between protons, electrons, and neutrons. Okay, so protons and neutrons weigh about 1 atomic mass unit each. Electrons weigh about nothing. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. That's the key takeaway from this. All right, so I mentioned atomic mass units. That's the scale on which we weigh atoms. Obviously, atoms are really, really tiny and very, very light. So the atomic mass unit scale is kind of a scale that's based on the mass of atoms. Originally, people used hydrogen to do it, but then because hydrogen's so tiny, there's a lot of variation, a lot of error that arose from using that. So people instead set the scale to carbon, figuring it's a pretty common element. So basically, a particular type of carbon atom is labeled as having 12 atomic mass units, and everything else is figured out from that. But essentially, it kind of more or less corresponds to the number of protons and neutrons in your atom. Okay, so I'm going to make the distinction between mass number and atomic mass in a little bit. But basically, they're kind of related. So let's talk about how these subatomic particles help distinguish between different atoms of different elements. That's the key skill I want you to get out of this. All right. So when you look at an atom and you look at the information about that atom, you can figure out the number of subatomic particles, those protons, electrons, and neutrons making it up. And vice versa. If you are given the number of protons, electrons, and neutrons for an atom, you can in turn figure out the information about that atom. All right, so what is this information I'm talking about? The two key pieces of information you need are the atomic number and the mass number. The atomic number is that number that you'll see your elements listed out under in order in your periodic table. I think I pointed out that if you look at your elements in your periodic table, numbered from left to right, top to bottom, they all go in numerical order. Right? Hydrogen is element number 1, helium is element number 2, lithium is element number 3, and so on. They all go in that order. That number is called the atomic number. Now, where does that come from? The atomic number is the number of protons in that atom. And so the number of protons is essentially kind of a fingerprint for the atom. If you know the number of protons in an atom, you now have identified what element that atom is. Okay? The two are inextricably linked. They are the same thing. So if you come across an atom with 6 protons, its element number 6, it has to be carbon. You're never going to find an atom of carbon that doesn't have 6 protons. Likewise, if you find any atom that has 6 protons, it has to be a carbon atom. That's how we identify these elements. Okay, and that's where the atomic number comes in. The other number I mentioned was the mass number. Remember, electrons don't really weigh anything. All of the mass of your atom comes from your protons and your neutrons. And each of those weighs about 1 atomic mass unit, right? So we use the mass number as an approximation for what the individual atom weighs. It's just the number of protons and the number of neutrons, and we treat each of them as weighing 1 atomic mass unit, and so the mass number is that total round number. Okay? Now please note that this means that a mass number has to be a whole number. It is never a decimal. You can't have half a proton or half a neutron. You always have to have a whole number for a mass number. Now you're probably saying to yourself, wait a minute, where are those decimals in my periodic table come from? If you look at your element and you say like, well, carbon typically has 6 protons and 6 neutrons, so that's 12, right? But why does the number next to carbon say 12.011? Where's that decimal coming from? I'm going to explain that in a little bit, but you'll find out that an individual carbon atom can have a mass number of 12. Carbon atoms in general can have an average atomic mass of 12.011. And I'll explain where that decimal comes from, but I'm pointing out here that mass number and average atomic mass are not the same thing. They're closely related. Okay, you have to use one to find the other, but they aren't the same thing. Okay, I point this out because a lot of students, this is a common mistake for students, where they will use the average atomic mass instead of a mass number when a question asks for the mass number. And that's often a common wrong answer for a lot of students. There are times when they are coincidentally the same thing or coincidentally similar numbers. Like in the case of carbon, if you happen to have an atom of carbon 12, it will have a mass number of 12 and its average atomic number is close to 12. But that's not always the case. Okay, so please watch out for that. Okay, so yeah, so for example, here we have an example of an oxygen atom with a mass number of 16, and this oxygen atom has 8 protons because it's element number 8, and it must have 8 neutrons as well to give it that mass number of 16. So 8 protons and 8 neutrons add up to that mass number of 16. So why is this an issue? Why are there where do these scenarios where the mass number and average atomic mass not being the same, where does that come up? Okay, why do we have an average atomic mass in general? The reason for this is because we have what are called isotopes. All right, I think back when I told you that and when you have a sample of an element, all of the atoms are identical to a certain extent. I was referring to the atomic number. All of your atoms of your sample of an element have the same atomic number. They all have the same number of protons. However, you can have atoms of the same element the same number of protons, but they might have a different number of neutrons, and therefore will have different mass numbers. Let me give you an example here. So over here we have 3 isotopes of magnesium. Okay, now why are they magnesium atoms? Each of them have 12 protons. So this atom over here has 12 protons, this atom has 12 protons, this atom has 12 protons. And by the way, since these are all neutral atoms, in addition to 12 protons, they also have 12 electrons, represented with little dots on the outside. However, these atoms of magnesium are not completely identical. The atom on the left has 12 neutrons. So with 12 protons and 12 neutrons, this atom has a mass number of 24. This atom in the middle has 13 neutrons. So 12 protons and 13 neutrons gives us a mass number of 25. And this one has 14 neutrons, so it has a mass number of 26. So even though these 3 different atoms have 3 different mass numbers, they're still all magnesium because they still all have 12 protons. Then that's what makes them magnesium, even though they don't weigh perfectly the same thing. All right, so that's where isotopes come in. Isotopes are atoms of the same element that have different mass numbers because they have different numbers of neutrons. Okay, so they all have the same chemical properties because they have the same number of protons and electrons, which electrons determine chemical properties. However, their physical properties might be a little bit different. Okay, they might have different densities, for example. Okay, for example, you may have heard of the term heavy water. It's used in nuclear power plants, and it just has certain like nuclear applications. Heavy water is water where the hydrogen atoms tend to be heavier isotopes of hydrogen, hydrogen 2 or hydrogen 3. So that's what makes that water a little bit denser and therefore a little bit more applicable for special cases like that. Okay, so that's what I kind of mean by isotopes having different physical properties. However, the chemical properties of those hydrogens are still the same. They still form water molecules the same way any other hydrogen atom would. So when it comes to displaying these isotopes, we have to write out we kind of put them in this format here, where we have a symbol, right, that 1 or 2 letter code representing the element. We write the mass number on the top left, and we write the atomic number on the bottom right, on the bottom left. Okay. When in doubt, just know the bigger number goes on top. Okay. So remember this this mass number over here is going to be your number of protons plus your number of neutrons. Whereas this number down here, your atomic number, is only the number of protons. All right? So you can use this information to figure out, again, if you have your number of protons, neutrons, and electrons, you can figure out this information. Or vice versa. If you have this information, you can figure out the number of protons, neutrons, and electrons. So quick note here, we're going to assume that all the atoms we're dealing with are neutral. We'll deal with ions in a later chapter. So for now, assume that however many protons you've got the same number of negative electrons to balance out those positive charges. Okay, so we'll assume they're the same number. Okay, quick note here about atomic numbers and how to write them out. You'll sometimes see chemicals written out just as, you'll just see the chemical symbol and just the mass number written over here. Okay. The reason for this is that sometimes the atomic number is left out because if you have a periodic table and you look up the symbol for your element, you can figure out the atomic number because it's there in your periodic table. Okay? Whereas the periodic table doesn't give you the mass number of an individual isotope. It'll give you the average atomic mass of all the isotopes of that element, and we'll talk about how to do that later on. But it doesn't tell you about an individual atom, which is what you need to figure out. So let's try a practice problem where we are going to determine where we can take this information about an element and figure out its number of subatomic particles, or vice versa. Okay, so I'm going to help fill out this table. I'll do the first couple of lines and walk you through them, and then I'll, I recommend pausing the video and trying the latter two yourself. Obviously, I'll continue that problem, but I recommend taking some time to see if you can do these on your own. Okay, so let's work through that first one together. So here we have the symbol H with a mass number of 1 and an atomic number of 1. Okay, so if you haven't memorized these yet, the symbol H stands for hydrogen. And we need to figure out the number of protons, neutrons, and electrons based on this information given to us in this problem. The first one that should be easiest to do is figuring out the number of protons. Remember, this is going to be the same as your atomic number. Okay, your atomic number of 1 tells you that there is 1 proton. Now, again, for this table, we're just going to assume everything's a neutral atom. So however many positive protons you've got, you have to have the same number of negative electrons to balance them out. So if you have 1 proton, there's going to be 1 electron. Okay, so far so good. The last thing left now is how many neutrons does this atom have? To figure this out, we have to look at that mass number. Remember, the mass number is the sum of the protons and neutrons combined. So 1 plus what gives you 1? 0. 1 plus 0 gives you 1, so there must be no neutrons in this atom of hydrogen. All right, let's try the second one together. So here we have fluorine. All right, if you have your periodic table out, but if you haven't, I really recommend doing that now for doing these problems. Look up fluorine. It's in the top right corner of your periodic table. Okay, so hopefully you found it, and you'll see that its symbol is F. Okay, so capital F for fluorine. Now, you'll also notice its atomic number written in over there in that in that box where that F is written, and you'll see that it has an atomic number of 9, which tells you it has 9 protons. Okay. Now, ignore the decimal. That's the average atomic mass for fluorine. That's not going to help you with this problem. Okay. It might coincidentally happen to be close to what you need, but it's not necessarily the number you need. Okay, electrons. How many electrons do we need? Well, if we have 9 protons, there must be 9 electrons to balance that out. So when we're writing out the symbol for fluorine, we're going to put an F for fluorine. If you want, in the bottom left corner, you can put 9 for the number of protons, so if you leave it out, it's okay. What do we put in the top left corner? What do we put for the mass number? Now again, don't use that decimal in your periodic table. That's the average of all fluorine isotopes. We want just this fluorine that the question's asking us for. So we have to look at our number of protons and neutrons combined. So there's 9 protons and 10 neutrons. That gives us a mass number of 19. Okay. Now, the number in your periodic table, that decimal happens to be close to 19. That's just a coincidence. Okay. This happens to be a very common isotope of fluorine. Not all fluorine isotopes have a mass number of 19, so do not use that decimal in your periodic table to figure out that 19. You have to use this 10 and this 9 to figure that out. Okay, so at this point, I recommend pausing this video and trying these last two. Use this information down here to figure out the symbols for and the names for these two examples. Okay, I'm going to continue on, but at this point, you might want to pause it and try it yourself. Okay, so hopefully you've taken a crack at this, but if you haven't, we start out with 29 protons. So you look at your periodic table and look up element number 29. Okay, again, all your elements are in numerical order. So getting to element number 29 hopefully should be relatively easy. It's somewhere near the middle of your periodic table. Okay, and you'll see that its symbol is Cu for copper. Okay, that's the name of this element. It's copper. And its symbol is Cu. If it has 29 protons, again, you should be able to figure out the number of electrons pretty easily. It's going to be the same number, 29. What is the mass number of this element? So we put down the symbol Cu, and in the top left corner, we're going to write 64, because 29 and 35 add up to 64. That's the number that goes up here. All right, let's try the second one. We have 1 proton, which tells us that this is going to be hydrogen. It's element number 1. If it's got one proton, it must have one electron. Now, you're probably saying, like, wait a minute, didn't we already do hydrogen? But notice that this hydrogen is different from this hydrogen. The first hydrogen example had no neutrons. Here we have one neutron. So what's the mass number going to be for our hydrogen isotope? Well, 1 plus 1 is 2. This is going to be an isotope of hydrogen 2. Oh, by the way, if you're referring to different isotopes of the same element, typically the way you do that verbally is you say the name of the element followed by the mass number. So this is hydrogen 1 and this is hydrogen 2. Okay, this is copper 64, this is fluorine 19, and so on. Okay, but here with hydrogen, you can see an example of what it looks like to have different isotopes of the same element. They're both hydrogen because they have one proton, but they are different isotopes because they have different mass numbers, which comes about from them having different numbers of neutrons. Okay. By the way, the common name for hydrogen 2 is deuterium. So if you ever hear that word, deuterium, it's referring to hydrogen 2. Tritium, by the way, is hydrogen 3. Those are just common names. You can call them hydrogen 2 and hydrogen 3. It's not a big deal. But if you ever hear about heavy water, it's water that uses deuterium and tritium instead of regular common hydrogen for making those water molecules. Okay, so I've been referring to average atomic mass quite a bit. Okay, and I think I've alluded to the fact that basically it comes down to an average of your different isotopes of an element. It's sometimes convenient to just use an average. However, if you want to use an average for all your elements, you can't just use a regular mean. The reason for this is that some isotopes are more common than other isotopes. And if you want to take a random sample of an element, you have to take into account this variation, or natural abundance as it's called, into account. Okay, because you want that average to truly reflect the mass of the sample you're taking. Okay, so when we say average atomic mass, the average we're using is not a mean. It is a weighted average, kind of like what we do for your grades. So just like your quizzes are not worth the same as your exams, your grade is weighted. In the same way, when we take the average for our isotopes, we weigh the average in favor of isotopes that have more of a natural abundance, so isotopes that have a larger percentage of the element. Let me give you an example here. So here we have chlorine. About 3/4 of all chlorine is chlorine 35. That's chlorine with a mass number of about 35 atomic mass units. Okay, so it's 75.78%, so about 3/4. The remaining quarter is chlorine 37, a heavier isotope, but one that makes up less of the natural abundance, the sample, a smaller percentage of all chlorine in nature. All right. So if you look up chlorine in your periodic table, you'll see that its average is listed as 35.45. Okay, where do they get that decimal from? How do they calculate that? It's a weighted average that takes into account that you have more of chlorine 35. That's why the average is skewed closer to 35. Okay, please note they didn't take 35 plus 37 divided by 2. That would be an average of 36. Okay, that's what we call a mean. We're not going to use that because it doesn't reflect the true average chlorine atom, because you're more likely to get a lighter chlorine atom than a heavier one. And that's why the average is skewed lighter than 36. Okay, so how do we calculate a weighted average? Okay, essentially what you do is for each isotope, you take its percentage and you multiply it by the mass of that isotope. You do that for all your isotopes, and then you add those numbers up. So in this example here, we would take our, if we took 75.78 over 100, because that's the percentage, and we multiplied it by 35 atomic mass units, which is about the mass of our chlorine 35, that would give us the contribution of from that chlorine. we would then do the same thing for our chlorine-37. We would take 24.22 over 100 times 37 atomic mass units, and we'd see what that number is. And then we'd add those two numbers up, and we would get 35.45, roughly speaking. Okay? So let me try that calculation out, and I can compare that, I can show that to you. So basically, if we take 75.78 divided by 100, or 0.7578, times 35, we would get 26.523 atomic mass units. That's a U, not an M. Okay. And if we take 24.22 divided by 100, okay, or 0.2422, and we multiply that by 37, we get 8.9614. Whoops, can't write it. 6 AMU. Okay, and if we add these two numbers up, we would get 35.45. Now, you might not get perfectly 35.45. There's going to be a little bit of rounding error in here. The reason for this is I assume that the mass of my chlorine-35 is 35 atomic mass units exactly. Remember, your protons and your neutrons don't weigh exactly 1 atomic mass unit. They're about that. So this number might not be perfectly 35. Okay, so that's going to change this number slightly. Likewise, this number is not going to be exactly 37, so this number will change slightly, and that's where they get this number from. You can use 35 and 37 as a quick approximation when you're doing this, but usually the question will give you the actual numbers. So let's see another example here. So remember, those three most common isotopes of magnesium are magnesium-24, magnesium-25, magnesium-26. Now, the majority of magnesium is magnesium-24, about 78.7% of it. And magnesium-24 actually happens to weigh 23.99 atomic mass units. So it's just under 24 atomic mass units. Okay, so if we multiply that by its percentage, we get 18.88 atomic mass units. Likewise, we're going to do that for each of the isotopes and multiply by their percentages. Okay, so if you add up these three percentages, you get 100%. Again, because that's kind of what's building up, most of magnesium. And when you get the mass contribution from each one of them, you add them up, you get an average of 24.31 atomic mass units. So if you look up magnesium on your periodic table, okay, it's towards the left, it's in that near the top of the second column. Okay, it's element number 12. You'll see that it has an average of 24.31 atomic mass units. But this is basically how they can calculate that number. Okay, so even though individual magnesium atoms have whole number mass numbers of 24, 25, or 26, the average magnesium atom would weigh 24.31 atomic mass units. Okay, and again, notice how that average is skewed towards 24, even though the mean of 24, 25, and 26 is 25. The reason for this, of course, is that the bulk of magnesium happens to be magnesium-24. So it makes sense that the average will be closer to 24. Okay? All right. So essentially, that's how you calculate weighted averages for any element. So if you are given this individual information about your isotopes, you're told what the mass of the isotope is and what percentage natural abundance it has, right? What is its percentage out of all of the atoms of that element, you can then work out what that average atomic mass is going to be. I mean, or the shortcut is you could just look that up in your periodic table as well. So that might be a quicker way to do that on a quiz or exam. But again, I'm going through the whole procedure for you because for those of you who are going to go on to Chem 111 and 112, you will be able to do this calculation backwards using the average atomic mass that you get from your periodic table. And if you have some of the information about some of the isotopes, you'll be able to work backwards and get missing information about one of the isotopes. You might be asked to figure out what is the what's the mass of one particular isotope, or what is the natural abundance of one particular isotope. You can work backwards to do that using algebra. I'm not going to get into that here. It's beyond the scope of this class, so those of you who aren't taking Chem 111 and 112, don't panic. And those of you taking Chem 111 and 112, don't panic either. Like I said, it's relatively straightforward algebra. If any of you are curious about that stuff and want to have a look at those types of problems, for those of you going on to Chem 111 and 112, I'd be happy to talk to you about that after class. So let's try a couple of practice problems right now to try this out. So here we have lithium, and we're told that it consists of two main isotopes, lithium-6 and lithium-7. Okay, so using the information in your periodic table, can you figure out which one of these has a higher natural abundance? Okay, which of these, in other words, is the more common of the two isotopes? Okay, the more prevalent one. So to save you the hassle of looking up your periodic table, I'll tell you right now, the average atomic mass of lithium is 6.941 atomic mass units. So you've got to ask yourself, is this number closer to 6 or closer to 7? Okay, notice that's 6.941. So it's only, a little bit away from 7, right? So that tells you that lithium-7 must be the more prevalent isotope. There must be more lithium-7. I mean, there's obviously a little bit of lithium-6, and that's why the average is lower than 7, but the fact remains that this average is still pretty close to 7, which tells you that must be the more abundant isotope. Okay, so let's try another practice problem. Okay, so here we have gallium, and you're told that gallium is made up of two main isotopes. You've got gallium-69 with an atomic mass of 69.926, and it makes up 60.1% of all gallium. You've got gallium-71, which has an atomic mass of 70.925, and that makes up the remaining 39.9% of gallium. What is the average atomic mass of gallium? Okay, so take a second and try this out. Okay, so feel free to pause the video here and try this one out. Okay, but here's how you'd work that out. You would take your percentage, right? So 60.1 divided by 100, or 0.601, and you would multiply that by that mass, 68.926. You would then do that for the second isotope as well. You would take its its mass and multiply it by its percentage, and then you would take those two answers and just add them together. Okay, so 41.42 plus 28.3. That should give you 69.72 atomic mass units. Or the shortcut, of course, is you could have just looked up gallium in your periodic table and seen right there that it has a average atomic mass of 69.72. So that would have worked as well. Okay, so again, on a quiz or exam, that might save you some time. Just like looking it up in your periodic table is a lot quicker than doing the calculation. But basically, that's how the calculation works. So we've discussed so far how the nucleus affects atoms. So your protons and neutrons, which houses the mass of an atom, affects physical properties like, essentially like mass and the identity of the element using, the number of protons. The chemical properties, of course, though, depend on the electrons. So while we can figure out the numbers of electrons in things, and we've done that up to this point, what might be more important now to understand this is how are those electrons organized? All right, and that's kind of the key thing I want you to get out of this next section. We're going to describe how electrons are organized within atoms. But in order to get there, to get into our description of this organization, I kind of have to give you another history lesson that kind of walks you through how we got to our modern understanding of electronic structure, of electronic configurations. All right, and to begin this sort of history lesson, I first need to talk to you about light. Now, light is a catch-all term that we use to really describe electromagnetic radiation. Okay, and this is a very diverse set of radiation. Basically, it includes things all the way down from low energy radio waves all the way up to high energy gamma rays. Okay, so you could describe this as electromagnetic radiation. And sometimes we'll use the term light kind of broadly in this context. People oftentimes, when you say light, they're usually referring strictly to visible light. That's the range of the spectrum that our eyes can pick up, and that includes the colors of the rainbow, which, when combined, appear to be white light. But you have to realize this spectrum extends beyond that. We have what's known as infrared light. So basically, if you look at the colors of the spectrum, the red end of the spectrum has longer wavelengths and therefore lower energy light, and violet light is higher energy. So infrared light, so to speak, is lower in energy than red visible light. So infra means lower than. Okay, so that's infrared radiation. It's lower in energy than red light that's visible. Ultraviolet, as the name suggests, is higher energy than regular violet light. Okay, and of course you can go beyond this. So if you go into lower and lower energy wavelengths, so longer wavelengths of these waves of energy. And by the way, a wavelength here is just, as the name suggests, it's the distance from one crest to another. So the length of one individual waveform. The longer wavelengths go down to things like microwaves and radio waves. Okay, and those are lower energy, right? So you're not going to get damaged by having a radio on or living near a radio transmitter. But if you go into higher energy wavelengths, so these are shorter wavelengths. You can see we can fit more arrays into these, because the wavelengths themselves are shorter. We start getting things like X-rays and gamma rays. Gamma rays are the highest energy of all electromagnetic radiation, and therefore the most dangerous. So if you get hit with a gamma ray, you'll suffer a lot of damage from the energy of that electromagnetic radiation. But anyway, this is how light travels, and understanding how light, or rather electromagnetic radiation, interacts with matter can give us an understanding of how electrons themselves are organized. It comes back to an original experiment where light from elements being passed through a prism give us a particular spectrum that we observe. And understanding why the spectrum came about was where we first started asking those questions about how electrons are organized. Okay, so basically, if you take white light, which is a mixture of different kinds of light on your electromagnetic spectrum, and pass it through a prism, you get the colors of the rainbow, right? You've seen this, you've probably seen this done just in a science class, or just in general, that when you pass light through a prism, it splits up into the individual wavelengths of light, into the different colors from the colors of the rainbow. And of course, this is how a rainbow itself works. Basically, if sunlight passes through water droplets, it produces an actual rainbow because those water droplets split up those colors. Basically, your different wavelengths of light travel at different speeds in glass. They get slowed down by different extents. So red light, which is lowest energy, gets slowed down the most, and violet light gets slowed down the least, and that's why they kind of spread out like this. Here's the interesting thing, though, that we notice when you don't use just regular white light, but if you use light that comes from an element, or a sample of an element that has been either heated up or has electricity running through it, instead of getting all of the wavelengths of visible light, you only see individual bands. Okay, so instead of getting a full rainbow, you just see certain lines. Okay, and the other really interesting thing here is that not only do you just see individual lines rather than the whole rainbow, but you also these lines are also different for different elements. All right, so you can see here we've got this bright line spectrum, or atomic emission spectrum, for strontium. All right, so when you heat up strontium or you pass electricity through it, it gives you this red light, and you pass that light through a prism, and it splits into these individual bands that we can see over here. Now, if you take barium, which is a different element, and heat it up or pass electricity through it, the resulting light, when split through a prism, will give you these different lines. Okay? So that's the interesting phenomenon that was observed with individual elements. If you took a pure sample of this element and heated it up, it produced light that, when split into a prism, didn't give you the whole rainbow. So why is that? What is it about individual elements that gives rise to these lines? And why are these lines different for different elements? Okay. Well, the first person to propose a plausible sort of explanation for this, or one that could actually help explain this relatively well, was Niels Bohr. So in 1913, Niels Bohr was a Danish scientist, eventually won the Nobel Prize in chemistry. But basically, he suggested that the way electrons are organized in atoms could account for why we're seeing these individual lines. So the way Bohr pictured the atom was kind of, again, going off the Rutherford model of the atom, where you have the nucleus at the center and you have the electrons in that extra nuclear region around it. Bohr suggested that the electrons could only inhabit set levels, or set quantum states, as he called it. So basically, instead of the electrons being able to occupy any place in that extranuclear region, there are only set places or set orbits that they could occupy. And they basically jumped from one orbit to another. So you imagine these circular paths that these electrons could occupy, and they could only exist in these set paths. And they jumped from one level to another. So when you took an element and you heated it up or ran electricity through it, you were providing energy to those electrons. And you were causing those electrons to jump to higher energy levels. They would jump up from a lower level to a higher level, but they wouldn't stay at that higher level. Eventually, they would have to relax back down. And when they relax back down, that energy's got to go somewhere. Where does that energy go? Well, it would leave as light. And that light that we see was the bands that you would see in your atomic emission spectrum, in your bright line spectrum. Okay? So essentially, the energy of the light that you saw, so you'd get light particles known as photons. That's another way to describe light instead of just waves. But basically, the energy of those photons would correspond to the energy gap that your electrons were traveling through as they relax back down. Okay? So for example, here we have a smaller energy gap resulting in an orange photon, so closer to the lower energy red side of the spectrum. And here a larger energy gap gives us a green photon, so it's closer to the violet or higher energy end of the spectrum. Okay? So again, there's various gaps that the that the electrons preferred to jump through, and that resulted in the different lines that we observe. Okay, so basically Bohr labeled these numbers, he just labeled the orbits with numbers, right? He called the principal quantum number n, and just them 1, 2, 3, etc., going further and further away from the nucleus. And we'll talk about that concept of principal quantum numbers a little bit later, something that we still hold on to in our common understanding of electronic structures. But basically, it's kind of similar to that concept of shells that you may have heard in another science class. But the bottom line is we have these energy levels, and as the number increases, you're getting further and further away from the nucleus. So if you want a picture of this, so this is kind of how Bohr envisioned the atom. You've got the nucleus in the center, as Rutherford suggested, and you have these set energy levels. Okay, so n1, 2, 3, 4, and so on, all the way until you get to n is equal to infinity, which is where you've removed the electron from the atom. All right, and so essentially what the electrons were doing was that they were jumping from one energy level to another when you provided energy to the atom, and it's when they relaxed back down that we would get different wavelengths of light corresponding to the lines of the bright line spectrum that we'd see. Okay, so that's how Bohr accounted for those lines that we would see in the spectrum. Okay, now the Bohr model of the atom is a very important way of understanding atoms. This was a very important stepping stone to getting to where we are now with how electrons are organized in atoms. I will point out that the Bohr model of the atom is just a stepping stone, though. We don't. There are things about the Bohr model that don't make sense. So, for example, this only works for atoms with one electron. Things get a little bit more complicated when you have more than one electron. So, this is not the best way to explain how all atoms behave. Okay, and there were a few anomalies with this explanation in general. So you're probably wondering, why do I bother teaching you something that I know is now incorrect? Well, again, that concept of principal quantum numbers, the fact that atoms or electrons only exist at set energy levels, these are things that we still hold to be true. And even in our modern understanding of electronic structure, these are still, provable true statements. Okay, and we're going to use those as we move forward with understanding how electronic configurations work. So moving on from Bohr, we built on the work of other scientists as well. There was the work of Louis de Broglie and Werner Heisenberg, for instance, that really comes to mind in terms of building our understanding a little bit further. Louis de Broglie was a French scientist who kind of showed that electrons moving really fast could be treated as waves. We could do the same math with electrons, as we do with light. Okay, which Planck and Einstein had already shown the converse with electrons. They'd shown that electrons, or I mean not with electrons, sorry, with light. Newton had shown that it acts in waves, and you can do all the math you do with waves with light. Basically, Planck and Einstein showed that you could treat them as particles as well, and that's where we got that concept of photons, right? Well, de Broglie just showed that you can treat light that way as well. Like we've always treated, you can treat electrons that way as well. We've always treated electrons as particles, going off the work of Thomson, but now you can still do the same math that you do with waves. You can do that with electrons as well. You can treat electrons as waves, all right? Werner Heisenberg was known for what's known as the Heisenberg uncertainty principle, that because electrons move so fast, you can't, it's kind of silly to try to understand to describe an electron's location and where it's moving at the same time. Basically, you can't measure its location and its momentum, because making one measurement for one of those will ruin the measurement for the other one. All right, so he said basically it's better to think of electrons in terms of probabilities of where they could be found. All right, if you want a kind of an analogy for that, it's like with a fan. If you have a three-bladed fan, and when the fan's off, you can see the individual blades, but when you turn the fan on, you can adjust the settings so you know what speed setting the fan's on, but the blades all look like a blur. You don't know where the individual blades are. So essentially what Heisenberg was saying was it might be better to just kind of think about just regions in space where these electrons are, rather than trying to pinpoint their location. All right, because you're losing information by trying to do that. So it comes down to a man named Erwin Schrödinger. So he was an Austrian scientist who kind of built on these ideas and developed what's known as Schrödinger's wave equation. All right, now this wave equation, involving a whole bunch of math that we don't have to get into in this class, but basically you can plug in information about an electron, known as its quantum numbers, plug that into Schrödinger's equation, and it will give you a region in space around the nucleus where you will find that electron. Okay? We call these regions in spaces orbitals. Okay, and this is the practical part that I want you guys to get out of this. We're going to describe these orbitals using numbers and letters. We'll use just a regular whole number, like 1, 2, 3, 4, and we'll use letters, things like S, P, D, F, and so on, to describe orbitals. And we're going to use that to explain where the electrons in an atom are located, which orbitals are housing which electrons. Okay, so that's how we describe an electronic configuration, and that's the key skill I want you to get out of this part of the lecture. Okay, so I mentioned that one of the holdovers from the Bohr model of the atom was that concept of principal quantum numbers. We still use those whole numbers, and like I said, it's kind of similar to that idea of shells. If you've ever heard of shells of electrons, these sort of layers of electrons in an atom, you're basically describing the principal quantum number. So the lower the principal quantum number, the closer you are to the nucleus. And generally, as you increase, you're getting further away from the nucleus and you're dealing with higher energy electrons. Okay? I mentioned that the other thing we use to describe orbitals are these letters, S, P, D, and F. Now, if that rings a bell, you probably remember earlier in this lecture where I talked about the blocks of our periodic table. Well, this is where those letters come from. And I will tie these two concepts together in a few slides. So you'll see how to use your periodic table to figure out your electronic configuration and vice versa. Okay. Generally speaking, S, P, D, and F lists the order of energies of different sublevels of electrons at a given principal quantum number. So, for example, a 3D orbital is higher in energy than a 3p orbital. Okay. Yeah, and there are certain levels we'll see that that don't even house particular orbitals. So, for example, the first principal quantum number only has s orbitals. So it's possible to have a 1s orbital, but it's not possible to have a 1p or 1d orbital. Those just don't exist. Okay, and that's just how the math works, which again, we're not going to go into detail because it involves calculus, which is beyond the scope of this class. So here's what those levels look like. Basically, or at least the ones that are possible, are your different quantum numbers. So here are your principal quantum numbers listed as energy levels, 1, 2, 3, and 4. So again, at the first level, there's only s orbitals. At the second level, there's only s orbitals and p orbitals. So this is 2s and 2p. At the third level, you can have 3s, 3p, and 3d. And it's only once you get to the fourth level that you start getting f orbitals. So 4s, 4p, 4d, and 4f. To be honest with you, we're probably not going to have to deal with f orbitals too much. We're not going to get into atoms that large. But just so you know, that's where they kind of show up. Okay, and we'll talk about the order in which we fill these orbitals in a little bit. Okay, so we use, you probably noticed we use little boxes here to represent the orbitals. Each of these individual boxes can hold 2 electrons, or a maximum of 2 electrons. And again, I'll talk a little bit about how that works in a second. You'll also notice that there's only one box for our s orbitals. For our p sublevel, or p subset of orbitals, there are 3 boxes. And I'll explain why that is in a second. And you'll notice there's 5 for d and 7 for f. We'll get into that in a second. So let's talk about those individually. So what do s orbitals actually look like? S orbitals are spherical in shape. They are a sphere that exists around the nucleus. And again, this is where you can find, if you're looking for orbital or electrons that are in a particular s orbital, they'd be somewhere in that spherical region. Okay, again, exactly where is not important. The idea is that they are somewhere in there. And to be honest with you, it's kind of better to treat it like it's everywhere in that region. Okay, it's like everywhere in that region at once is kind of the idea that you get out of the Heisenberg synergy principle. It's like using my fan analogy, right? If your fan's turned on and the blades are spinning, you don't want to stick your finger anywhere in that blur where the blades are, because you're going to hurt your finger. It doesn't matter which part of that blur you stick your finger in, you're going to get your finger your finger's going to hit the fan, and you don't want that. So it's kind of like that with orbitals. It's probably better to just treat the electron as being everywhere in that sphere at once. Okay, now the cool thing with I think I pointed out earlier that electron or orbitals can hold 2 electrons. Each of those boxes we had representing an individual orbital can hold a maximum of 2 electrons. Now you're probably saying to yourself, wait a minute, electrons are negatively charged. Won't sticking 2 electrons right next to each other be a bad idea? Won't they just try and repel each other? And you'd normally be right. The 2 electrons don't like being right next to each other. What gets around this issue, or at least like minimizes it, is that there is a property of electrons in that they sort of we call it their spin. But basically, if you have two electrons with opposite spin, they don't repel each other as much. So if one's spinning one way and the other spinning the other way, they can be housed in the same orbital, and it's not as bad, I guess, not as energetically disfavorable as you would think it would be by having two like charges trying to get away from each other. All right, so now with p orbitals, I pointed out that for a p subset of orbitals, we show 3 boxes. The reason for this is that there's actually 3 orbitals within your p subset of orbitals. And so that p subset can hold a maximum of 6 electrons, each of those orbitals holding 2. Now, how are we able, how do these 3 orbitals interact? Well, in the case of p orbitals, they look like this sort of dumbbell shape. And these dumbbells are kind of oriented in 3 different directions, in your x, y, and z directions, as you can see here. So this is trying to draw a 3D coordinate system on a 2-dimensional slide. So you kind of have to visualize this in 3 dimensions here. But you can imagine that the z-axis is going straight up and down in the plane of your paper or in the slide you're looking at, with your x and y directions, one lobe's kind of sticking towards you and the other one's sticking kind of away from you. Okay, so all of these 3 axes are at 90 degrees to each other. All right, and that's where each of those orbitals are located. Okay, so let's say you have a 2p subset of orbitals. You have 2px, 2py, and 2pz. And each of them can hold a maximum of 2 electrons, so the combined system can hold a maximum of 6 electrons. All right? Yeah. With d orbitals, I pointed out that there are 5 in a d subset. There are 5 different directions that your d orbitals can be oriented. So you have dxy, dyz, dxe, and so on. You don't need to memorize the names of these. And again, to be honest with you, you probably don't even need to think at this level for this class. Again, the important thing to get out of this is explain where the electrons are. So as long as you can show, you can name your d subset of orbitals as like 3d or 4d or whatever, and say how many electrons are in there, for a maximum of 10 electrons. That's kind of the key thing to get out of this. All right. I don't have a picture of f orbitals. They look pretty trippy. Again, way beyond the scope of this class. Don't worry about what f orbitals look like. So how do we fill up these orbitals? How do the electrons get into these orbitals and start filling them up so that we can start describing them? There are 3 rules that we use to describe this, and I've kind of alluded to one of them already, and that's the Pauli exclusion principle. I pointed out that if you have 2 electrons in an orbital, they have to have opposite spins because otherwise they would repel each other. This is the Pauli exclusion principle in a nutshell. The technical definition is that no 2 electrons can have the same 4 quantum numbers, because that would imply they're the same electron. That's a way more technical definition than you really need. The key thing to get out of that is if you have 2 electrons in an orbital, they have to have opposite spins. That's what that effectively means. All right, so we represent these electrons using arrows. So when you draw electrons in an orbital, in a box representing an orbital, we draw one arrow pointing downwards and one arrow pointing upwards to represent our 2 electrons with opposite spins. Okay. So when we start filling up electrons in our orbitals, we have to keep on filling them up. Basically, we follow what's called the Aufbau principle. I'll get into that in another slide, but essentially, you can't go to a higher energy level until your current energy level is full of electrons. So every s orbital can hold a maximum of 2 electrons. Every p subset of orbitals, okay, which remember has 3 orbitals in it, can hold a maximum of 6 electrons. Okay, your d sublevel can hold 10, because remember there are 5 orbitals, 5 different directions, and if each of them holds 2, that's 10. And the f sublevel can hold 14. Now, if you're having trouble remembering this this is where your periodic table can help you. All right. Remember, if you look at your different blocks of your periodic table, your S, P, D, and F blocks, okay. If you look at your periodic table, you'll notice that your S block has 2 columns. That's because each s orbital can hold a maximum of 2 electrons. Your p block is 6 columns wide because the p sublevel can hold 6 electrons. Likewise, your d block is 10 columns wide and your f block is 14 columns wide. The other way to remember this is that each orbital can hold 2 electrons, and the number of directions or the number of orbitals you have at each sublevel is just the odd numbers. So 1 times 2 is 2. The next odd number is 3. 3 times 2 is 6. The next odd number is 5. 5 times 2 is 10. And the next odd number after that is 7. 7 times 2 is 14. Okay. Again, whichever way you use to remember the maximum capacity of each sublevel is up to you, but that's something you do have to remember. How many electrons can each sublevel of orbitals hold? Okay, so we're going to get into representing these. I'll explain the rest of the rules. So we've already talked about the Pauli exclusion principle, and I've alluded to the Aufbau principle. I'll explain these in a little bit, but what we're essentially going to get to is we want to describe these orbitals using a number and a letter. We use a number representing the principal quantum number, and we use a letter representing the type of orbital. Okay, and we want to say where the electrons are in these orbitals. Okay, so we can do this in 2 ways. We could write out electronic configurations where we represent the number of electrons as a superscript. So for example, if we have a 1s orbital with 2 electrons in it, we would write it out as 1s2. Okay? Or we could draw orbital diagrams. I could draw that 1s orbital as a box. Okay? I could say, okay, here's my 1s orbital, and there are the 2 electrons in it represented with these 2 arrows, one pointing up and one pointing down. All right? So those are different ways we can show whether electrons are in an atom. So let's talk about the rules that we follow when writing out these electron configurations. So we're going to draw what's called ground state electron configurations. These are sort of the natural or most stable states of atoms. Okay, there are some special cases out there which you don't have to worry about, but basically you could have excited state electron configurations, where you add extra energy into a system. For now, just assume that every atom you're dealing with is in the ground state. So what does this entail? Why do atoms look this way? The reason for this is things in nature tend to seek out the lowest energy. All right, and so when you're trying to, if you were trying to build an atom from scratch and you were adding electrons to it, they would occupy the lowest energy orbitals first before building up to higher and higher energy orbitals. This is called the Aufbau principle. Aufbau being a German phrase meaning building up. Okay. Basically, the idea is that you have to fill up your lowest energy orbitals first, and it's only when they're full that you move to higher energy orbitals. Now, in what order do these orbitals fill? If you were to look at your different orbitals, you would notice that you would start off with your 1s orbital, that's the lowest energy orbital, okay, and it can hold 2 electrons, right, like all s orbitals do. So when that's full, you move on to your 2s orbital. Okay, it makes sense. After 2s comes 2p, so we're still on the second quantum number, second principal quantum number, but remember, you can now start having p orbitals at that second level. When that's full, you go to the third level, which has a 3s orbital, so you fill that first. Then comes 3p. Now this is where things get a little bit weird. Normally you would think that after 3p would come 3d, but it turns out that the 4s orbital happens to be lower in energy than 3d. It just turns out that the gap between 3s and 4s is smaller than the gap between 3p and 3d, and so 4s orbital just happens to be lower in energy, and according to the Aufbau principle, it needs to fill up first, and that's what we observe. Okay, so we fill up the 4s orbital and then the 3d orbital. Then comes 4p and so on. Okay, and so you need to remember this off-bound principle when we're writing out electronic configurations. Now, how do you remember that? How do you remember these weird quirks like the 4s orbital coming before the 3d? There are two ways to do it. I'm going to show you both methods. You can pick one and just use whichever one you like better. Okay, I'll teach the second method a little bit later on when we start getting to a practice problem, because it'll involve me using a periodic table to show you. But for now, let's start with that first method, and that's using this diagram over here. Okay, so if you were to Google off-bound principle, you'd often see this diagram. This would probably be one of the first diagrams that pops up in a Google image search for off-bound principle. And the reason for this is a quick and easy way to remember the orbitals and the order in which they fill up. Okay, so if you were trying to draw this yourself, I'm going to show you how to draw this. If you were just, you didn't have the diagram in front of you and you wanted to try drawing it out, essentially, you start off by writing out all of your orbitals. So I start off with my 1s orbital, then 2. So let's do all my s orbitals. So 2s, 3s, 4s, 5s. You could keep going, or you could stop wherever you need to. You probably don't need to go all the way up to 7s, but let's say we do. Okay, then let's do our p orbitals. Now remember, p orbitals only start at the second level onwards. So 2p, 3p, 4p, 5p, and so on. Okay, you can keep going. 6p, doesn't matter. Then come d orbitals, which remember, d orbitals only start at the third level onwards. So 3d, 4d, 5d, 6d, and so on. Okay, you could then start with f orbitals, which of course only happen at the fourth sublevel, or fourth principal quantum number. So 4f, 5f, and so on. Okay, I could keep going. Really, with enough energy, you can keep on going to infinity. I'm just going to stop here because I just want to illustrate how you would fill this up. To be honest with you, most of the examples you're going to do are going to be down here. So you really don't have to build this diagram all the way up to the 7th level or whatever. Okay, so how do I remember the off-bound principle? What order do my orbitals fill in? So first, I fill in this s orbital. Okay, I'm going to draw arrows going to the top left, the northwest, if you will, to remember which order these orbitals fill in. So first, I fill in my 1s orbital. That's my first orbital that fills it. When that's full, the next orbital is going to be 2s. After that's full, I go to 2p, and when that's full, I go to 3s. When my 3s orbital is full, I then fill up 3p. And now you can see where this is going to go next. When 3p is full, we go to 4s. See, this is that weird, exception that we saw, that weird deviation from what you would have expected. So after 4s is complete, then we fill up 3d. And after 3d comes 4p. After 4p is full, comes 5s, and so on. Okay, and you can keep on going accordingly as you need to build up, bigger and bigger atoms. All right. Now, don't forget, of course, each of these orbitals, these sets of orbitals, have different numbers of electrons it takes to fill them up. S orbitals can hold a maximum of 2. P orbitals can hold a maximum of 6. D orbitals can hold a maximum of 10, and F orbitals can hold a maximum of 14. Okay, so an orbital's got to fill up before you can move on to the next energy orbital. That's the off-bound principle. Okay, the analogy I use to describe that to students is it's kind of like pouring a glass of water. When you pour a glass of water, you have to fill up the lower energy, like the bottom of the glass first, and as you add more and more water, it starts building its way up the glass. You're never going to pour a glass of water and see water at the bottom of the glass and then a gap and then water at the top of the glass. Okay, so likewise, it doesn't make sense to start filling up one orbital and then jumping to a higher energy orbital without first filling up the ones in between. Okay, so that's the concept of the off-bound principle. All right. The last rule when it comes to filling up these orbitals, so besides the Pauli exclusion principle and the off-bound principle, the third rule that we see is what's called Hund's rule. All right, Hund's rule only applies to how orbitals that are degenerate fill up. Now, what do I mean by degenerate orbital? Degenerate orbital, the word degenerate here refers to same energy or equal energy. Okay, it's not degenerate in the in the more colloquial term. Okay, so it's not like it makes bad decisions or something like that. But basically, a degenerate set of orbitals is a set of orbitals that have multiple orbitals at the same energy, like a p orbital or a d orbital or an f orbital. Okay, how do we put in our electrons into those subsets of orbitals? Well, Hund's rule states that electrons like to space out before they start pairing up. The analogy I use here is kind of like a bus. Imagine that you've got a public bus with 3 seats on it. So let's say we're going to use a p orbital, a subset of p orbitals, to represent our our crowded bus. Okay. So anyway, so let's show you the. I'll get to the p orbital in a second and illustrate that. But remember, with the Aufbau principle, you want to build up your way to those orbitals, right? So let's say I've put my first electron and my second electron to my 1s orbital. It's now full. I then go to my 2s orbital, which takes a third and a fourth electron. It's now when we start putting our fifth electron onwards that we get to our degenerate set of orbitals. So here's our 2p subset of orbitals. I've drawn it here with a little bit of a gap to make it a little bit easier to see. I find that a lot of people, when they're trying to draw them by hand, tend to draw them together as one box like this that's divided. So that's how they would draw their 2p orbitals. Okay. Likewise, you probably noticed that in my diagrams, I've used regular double-headed arrows. Most people, when they're drawing this by hand, like to use single-headed or fishhook arrows. It's just easier to fit them into these boxes. Okay, like that. So again, picture this 2p subset of orbitals as a bus with 3 seats. Now, each of these seats, they're like bench-style seats, can hold a maximum of 2 people. Okay, so how do people get onto the bus? How do they fill up these seats? So the first person gets on the bus, and they take a seat. That's pretty straightforward. Second person gets on the bus. Where is that second person going to sit? Is he going to sit next to the stranger in that first seat? Or is he going to take his own seat that's available to him? Well, again, remember, these are strangers. No one knows each other. They don't like sitting next to each other. So since these 2 seats are at the same energy, they're completely equal in all respects, this person is going to take the second seat, right? And this is not violating the Aufbau principle, because remember, these 3 orbitals are degenerate. They're the same energy. So it's not a violation of the Aufbau principle to have these electrons spread out. All right, that's why, again, I think a lot of people prefer drawing these 3 boxes like this when they're drawing them by hand, to help remind them that these 3 orbitals are degenerate. Okay, so that when you're drawing this by hand, that second orbital is going to go into that second box. Okay, or sorry, that second electron is going to go into that second orbital. Okay, that box representing that orbital. Okay, third person gets onto the bus. Where they're going to go? Well, same thing, right? They see that empty seat over there, right? The empty seat over here. So they're going to take up that third seat. It's only when the fourth person gets on the bus, or the fourth electron starts filling up that orbital, that they now are forced to pair up. So that fourth one now has to take up this. It has to pair up with this electron here. All right. It does not jump to the 3s orbital, because again, that would violate the Aufbau principle. That 3s orbital is higher in energy than your 2p. You can't start filling up that 3s orbital until that 2p subset is full with 6 electrons. Okay? So, yeah, so the 4th, 5th, and 6th electrons fit in there. It's only once this orbital is full, now you start putting electrons into that next 3s orbital. All right, so those are the 3 rules for writing out electronic configurations. You have the Aufbau principle, which states you've got to fill in electrons from lowest energy orbitals all the way up to highest energy orbitals, but you can't skip any. You have to kind of work your way up there. Okay. You have the Pauli exclusion principle. So when you have 2 electrons in an orbital, they have to have opposite spins. Okay, so you draw them with an up pointing arrow and a downward pointing arrow. And then the third one is when you have degenerate orbitals, that's p, d, or f orbitals, you use Hund's rule, where you spread out the electrons before you start pairing them up. Now, Hund's rule and the Pauli exclusion principle, you only really observe them when you are drawing out orbital diagrams. If we are writing out regular electronic configurations, really the off-bound principle is kind of the most important thing out of all of these. Okay, so that's the one you really want to keep in mind. So don't stress too much about Hund's rule and the Pauli exclusion principle, but those are also rules that you have to follow if you were drawing an orbital diagram. Okay. So, as I pointed out earlier, when we're drawing out these diagrams, we use little boxes representing them. So your s orbitals draw one box, which can hold a maximum of 2 electrons. Your p orbitals is a set of 3 boxes, which I've kind of drawn a little slightly separately just for clarity, but a lot of people, when they're drawing them by hand, will draw them together. Likewise, d orbitals have 5 of these boxes, which again you can draw smushed together if you like. And f orbitals have a maximum will have 7 boxes. And again, you're probably not going to have to deal with those, so don't panic. Okay, so how do we use this? How do we describe the electrons in an atom, using these orbital diagrams or using electronic configurations? Well, remember, you can get the number of electrons from the atomic number of your element. Well, technically the atomic number is the number of protons, but again, assuming that these atoms are neutral, they should have the same number of electrons. So using that and the off-bound principle, you can start building up, to whatever number of electrons you're trying to account for. Once you've got the right number of electrons, you can just stop. All right, so if let's say we've got a hydrogen atom, that's the simplest atom there is. It has 1 electron. Where's that 1 electron found? Well, remember, that 1s orbital is the simplest orbital. So that 1 electron is going to be in that 1s orbital, which is represented with 1 arrow. Okay? Now, if I wanted to write that out in electronic configurations, I would write that out as, I would say, okay, that's a 1s orbital, and it's got 1 electron, so I would put that 1 as a superscript above it. Okay? So next we have helium. Helium is element number 2. It's got 2 electrons. So if we were drawing that out, we would draw 2 arrows, one pointing up, one pointing down, because again, we want to show the Pauli exclusion principle there. Okay? And so if we were writing out its electronic configuration, we would write that out as 1s2. Because there's 2 arrows or 2 electrons in here, and so we would have to put that superscript of 2 over there. Okay? Then we have lithium. Lithium has 3 electrons. What does that look like? Well, the first 2 go into that 1s orbital, just like with helium. But remember, s orbitals can't hold more than 2 electrons. So that 3rd electron has to go to the next energy level, which would be that 2s orbital. And so you put that 1 electron in there. Now, we've accounted for all 3 electrons. How would we write this out as an electronic configuration? We would write that as 1s2, because there's 2 electrons in that 1s orbital, and we'd write 2s1, because there's 1 electron that we represent with a superscript. Okay? And if you want to check your work, by the way, again, remember, the number of electrons, which should be these superscripts added up, or these number of arrows added up, should equal the number of electrons you're trying to represent. Okay? So you probably noticed the way I said that verbally. Typically you say the number and letter of your orbital, and then you say the number of electrons in that orbital. Okay, so I said for lithium it was 1s2, 2s1. Here is the electronic configuration for carbon. Okay, carbon is element number 6, so it has 6 electrons. So we should show those 6 electrons accordingly, with 2 of them in that 1s orbital, 2 of them in that 2s orbital, okay, and the remaining 2 must go into that 2p orbital, which is next in energy. Okay, so even though that p orbital can hold a maximum of 6 electrons, we only need 2 more electrons to get the total 6 electrons that we need. So 2 plus 2 plus 2 is 6 electrons in carbon. Now, if we were saying this verbally, we would say this as 1s2, 2s2, 2p2. Okay? So I know that might sound a little confusing when you're saying it verbally, so you kind of have to get that cadence down. Like, it's like, like number and letter of orbital, and then number of electrons. Number and letter of orbital, number of electrons. Number and letter of orbital, number of electrons. Okay? Now, this is the full electronic configuration. There is a way to write an abbreviated version using a noble gas to represent the core electrons. I'll show you how to do that in a little bit. Okay, but it's kind of silly for some of these smaller ones, but it is useful, especially once you get to the bigger ones. Okay, so in these next few slides, I've kind of shown the orbital diagrams and the electronic configurations for, a bunch of elements just going in numerical order, in order of atomic number. So we'll work our way up accordingly as we go in. So here we have hydrogen and helium. Here we have the entire second period. Okay, so here are the diagrams. Again, you can see Hund's rule in action with these degenerate p orbitals. Okay. And you can see how the electron configuration is written out. Notice that in orbital diagrams, we show the individual boxes, but we don't have to do that for the electron configuration. We can just say the total number of electrons at that sublevel. Okay, so I don't have to say 2px, 2py, 2pz. I can just say 2p, and here's the total number of electrons that are in all three of those boxes. Okay. By the way, I mentioned those the orbital notation, or the noble gas notation that kind of abbreviates this. So here you can see that I've kind of taken away those core electrons of helium, and that are found in that 1s2 orbital, and I've kind of swapped it out for the symbol for helium. All right. Again, it's kind of silly for the second row because helium only takes up 2 electrons, and so you're writing up as much, you're taking up as much space to write helium as you are to write 1s2. So it is kind of silly for this first row because it really isn't abbreviating things much. I'll go through an example on the next slide with the third period. Okay, so here we have that third row of elements, and again you can see how we've accounted for all the electrons. Here are the full electron configurations. To save space, they didn't bother putting the 10 electrons from neon. They only continued from that 3s orbital onwards. Okay, and that's to save space, but again, this is also useful when we're writing out electron configurations. It helps us take up less space when writing these out. All right. The reason for this is that really, oftentimes you're only concerned with those outermost electrons, that highest energy level. Okay, because those are the electrons that your atom's going to use to do its chemical bonding. All right, so in the case of our sodium atom, it's this 3s1 electron that we mostly care about. That first and second level aren't really doing anything, So if we only want to show this 3s orbital, we can kind of hide these core electrons, these electrons that are lower down in energy. Okay, so what we do is we use the noble gas that comes before sodium. So we go to the previous row, so we go to period 2, and we use the noble gas at the end of it, which is neon. All right, neon accounts for these 10 electrons. Okay, so we can, instead of writing out 1s2, 2s2, 2p6, which actually if I go back a slide, you'll see that's the electronic configuration of neon. Okay, instead of writing that out fully, we're going to basically swap that out and write out the symbol for neon in square brackets like that. Okay, and that's why, and we just continue from there. So here's the 10 electrons from neon. There's an 11th electron in that 3s1 orbital, which comes after neon, and that accounts for the 11 electrons in sodium. Okay, and again, you can see we've done this for all of them. We're just accounting for what beyond those 10 electrons are present. Though, of course, you could write out the full configuration this way. Okay, and don't worry, we'll do some more practice so you can see how this works. Okay, I mentioned earlier that the Aufbau principle is the most important rule to take away from this, and for those of you who don't like that diagram I showed you how to draw, there is another method to use where you can use your periodic table to figure out the Aufbau principle. It turns out that your elements fill up the periodic table according to the Aufbau principle. Because the Aufbau principle is a kind of fundamental way that atoms get built up. So you could look at the way your periodic table is organized to help remember the Aufbau principle. Okay. Now to do this, you need to pay attention to the row numbers, the number of periods in your periodic table, and you need to pay attention to those blocks I mentioned, your S, P, D, and F blocks. As you build up to the element you're looking for, you're going to go through different elements on your way up there. Pay attention to what blocks and what rows you're in, and that will correspond to the orbitals you're filling up on your way upwards. So keep that in mind, that you've got your S, P, D, and F orbitals, and we're going to also keep track of the rows that we're going through. Now, quick note here about the rows. The main group elements, that's in the S and P blocks, will have their numbers correspond to the actual row you're in. With the D block, the number is going to be one lower than the row it's in. Okay, so I've noted that with n minus 1. Okay, so if you're in the fourth row, you're actually going through the 3D orbitals, even though on either side of it you have 4s and 4p. This again corresponds to that weird quirk we saw in the Aufbau principle, where that 4s orbital happens to fill up before your 3D orbital does. Okay, your F block, by the way, drops 2 numbers, but once again, you're probably not going to have to worry about writing out configurations with F orbitals. But in case you ever do, just note that the numbers are 2 lower than whatever row you're in. So let's look at our periodic table and see how this works. So if we are building our way upwards, we would first go through the first 2 elements, hydrogen and helium. Okay, so here's our different blocks, S, P, D, and F. All right, and the first 2 elements we go through are hydrogen and helium. Well, they're in the first row. It's, even though helium is put over here on the right with the noble gases, because it is a noble gas, the reason it behaves like a noble gas is because its s orbital is completely full. All right, so it's put here with the noble gases for chemical reasons. It has the same chemical properties as the other noble gases, but from an electronic standpoint, you could imagine helium kind of being here. So imagine helium is actually over here. It's the second element in that S block. All right, though obviously it should go here with the other noble gases from a chemical standpoint. So anyway, my point here is that you've gone through the first row and the S block, and that's because the orbital you're filling up here is that 1s orbital. Okay, so 1s orbital. So what comes after helium? Well, you go through lithium and beryllium. Now notice you're in the second row. All right, you're in that second row, and you've got that S block still. You're still in that S block. So that's 2s. Next, when you go through boron through neon, you're still in that second row, but now we're in the P block, right? This whole thing is the P block. So this is 2p. All right? After 2p comes 3s. Okay, third row in S block. After 3s comes 3p. After 3p comes 4s. Now notice where we're going next. We're going to the D block. But remember, even though you're in the fourth row, we've got to drop a number for the D block. Okay, so that D block is, the D block is going to be 3D, even though it's in the fourth row. So it's 3D. And then, of course, the P block, you just keep the regular numbering, so it's 4P. Okay, I'm saying this verbally, but for those of you who've got that diagram out for your Aufbau principle with the little like diagonal arrows, you'll notice that we're still filling up the orbitals in the same order as that diagram. Okay, so after so just to continue from where I left off, after 4p comes 5s, then 4d, 5p, 6s. Now this is where we jump to the F block. So, and we drop 2 numbers. So 4f, 5d, 6p, 7s, drop 2 numbers, 5f, 4, sorry, 6d and then 7p, which isn't shown here, but it would continue on. And again, don't stress about some of those heavier elements. You're not going to go that far usually. Okay, so whether you like using that diagram with diagonal arrows or you like using a periodic table, pick whichever method you find easier to help you remember the Aufbau principle. Okay, that's the order in which you want to write out your electrons in order to write out electronic configurations. So let's practice this. Let's write out a couple of examples, or go through a couple of examples and see how to apply these electronic configurations. Let's start off with chlorine. Chlorine is element number 17, so we want to account for the 17 electrons in a neutral atom of chlorine. The answer is here in front of us, but let's walk through how we get that answer. So, if you locate chlorine, and again remember all your elements are in numerical order by atomic number, so there's element number 17, chlorine, we want to build our way upwards to that chlorine atom. So the first orbital, of course, that you go through is that 1s orbital. Okay, so build up 1s with 2 electrons. Okay, so let me write that out as we're doing it so that you can see how we work through this. So we're going through that 1s orbital, okay, and we're going through both elements in that, so it's 1s2. After that comes that second row, and we're going through the s block, so it's that 2s orbital. Okay, and again we're going through both elements in that 2s block. So we've gone through 4 elements so far on our way through beryllium, and that's 1s2, 2s2. But we haven't reached chlorine yet, so let's keep going. After 2s comes 2p. We're in that second row in that p block, so we would write that out as 2p. Now notice that we're going through all 6 elements of that p block, so it's 2p6. All right. Next, we're going to go to the third row and the s block, so that's 3s. So we would write 3s, and we're going through both elements in it, so it's 3s2. Because again, remember, those s orbitals can only hold a maximum of 2 electrons. After that, we've filled the 3s orbital up. We want to continue on. We're still in the third row and in the p block now, and we're going to fill up that orbital on its way towards chlorine, but we're not going to fill it up completely. We only go 1, 2, 3, 4, 5 electrons, and we've hit chlorine, so we kind of stop there. So we write out those 5 electrons as 3p5, and there you have your electronic configuration that we had on the previous slide. Now, if you want to check your work, there's 2 things you can do to check to see that we've got the right answer. Your superscripts should add up to your total number of electrons. So 2 plus 2 plus 6 plus 2 plus 5 adds up to 17 electrons, which makes sense. We want 17 electrons for chlorine. The other thing you can do to check that you've got the right answer is that your last orbital should point out the location of the element in question. So chlorine is located in the third row and in the p block, and it's the 5th element of that p block. So we're in the third row, we're in the p block, and 1, 2, 3, 4, 5 elements. So that's a quick way to check your work. All right, that should agree, and the total number of electrons should agree. Okay, now for those of you who like the other method of the Aufbau principle, using that diagram, you'd still fill this up the same way. You'd probably notice using your diagram, so if I were to write that down here, 1s, 2s, 3s, okay, and I'd have 2p and 3p, okay, I fill up my 1s orbital first, and remember, that can only hold a maximum of 2 electrons. So I write 1s2. After that comes 2s. And again, that can hold a maximum of 2 electrons, 2s2. Now keep in mind, we're going to 17, so 2 and 2, I've only got 4 of my 17 electrons. So I want to keep on going. After 2s comes 2p. That's got 6 more electrons, so that's 2p6. Okay. And that still hasn't gotten me to 17 electrons yet, so I continue on to 3s. Okay. So again, if I fill that up with 2 electrons, 3s2, I've got 2, 4, 10, 12 electrons. I still haven't reached 17. So finally, the next orbital I fill up is 3s, 3p, and of course that can house, since that can hold a maximum of 6 electrons, I only need 5 more. I will put all 5 of those electrons in that 3p orbital, and that's where I would stop. Okay. Now, a quick note here for those of you trying to write out a noble gas configuration for this. To do noble gas notation, you want to continue from the previous noble gas, right? So if we have chlorine over here, okay, where's the previous noble gas? So you go to the previous row, and remember, noble gases are always in this last column, in column 18 or 8a, depending on which type of periodic table you're using. So the noble gas we're using is neon. Okay, neon has 10 out of our 17 electrons. Okay, so we would write this out. We would start off by writing neon, or Ne, in square brackets, and we would continue for the remaining 7 electrons. So if you're using the periodic table method, you would continue from there. So after neon, okay, which is in the second row in the p block, we continue with 3s. Okay, so there's 3s2, and then continue on from there. The last 5 would be 3p5. Okay, and that accounts for our 17 electrons in our chlorine. And again, you can check your work the same way. The only, that last orbital, 3p5, is still going to be the same. The other thing to notice is that your total number of electrons will still add up to 17. You just have to remember that neon has 10 electrons. I'll write that a little bit neater. So neon has 10 electrons. Okay, so 10 plus 2 plus 5 is 17 electrons. Okay, for those of you who like using your Aufbau principle diagram, remember your noble gases always end on the p block. So you have to realize that you're using neon, and since it's in the second row in the p block, you would continue from 2p onward. So after 2p, we have 3s, and again, that's where 3s2 comes in, and after that comes 3p, which is why 3p5 comes in to get to our 17 electrons. Okay, so which again, I've kind of described both methods. Please don't use both methods. You'll probably get confused if you try to remember both. Just pick one that you find easier and stick to that method. That's my advice when it comes to writing out these electronic configurations. Again, this probably seems like a bit of a clunky process when you first start this out. Again, I recommend practicing this more to really get the hang of it. Okay, so with that in mind, let's try another example. Oh, by the way, if you want to see this written out as an orbital diagram, here's what that looks like. So we're going to draw in our 17 electrons. So the first two go into that 1s orbital. Next two go into that 2s orbital. Then with the 2p orbital, we're going to fill it up with following Hund's rule. So 5, 6, 7, 8, 9, 10. Okay, then the 11th and 12th electrons go into the 3s orbital, and then the remaining 13, 14, 15, 16, 17 electrons fill up that 3p orbital, but we'd stop there because that's 17 electrons. Okay, so you do not put another electron to pair up this orbital in the 3p subset, because then you would be 3p6, not 3p5. Okay? All right, so let's try another example out. Let's try doing calcium. So calcium is going to be very similar to chlorine. It's a little bit bigger. It's got 20 electrons instead of 17. So let's try that one out. Okay, if you'd like, you can pause the video here to try this out by yourself before I show the answer. But yeah. Okay, so if you've hit play again now, you're probably listening to me explain this. So here we have calcium. All right, so you want to account for the 20 electrons leading up to that calcium. Okay, so again, depending whichever method you use, if we're using our periodic table, we go through 1s, and that has 2 of those electrons. Then comes 2s, which has 2 more electrons. Then comes 2p with 6 electrons. Then 3s with 2 electrons. And 3p with 6 more electrons. Again, that's 18 of our 20 electrons so far. And the last 2 electrons are in our 4s orbital. So 4s2 is what you would end with, which again makes sense. You should end up in the fourth row in the s block, and your calcium is the second element in that block. Okay, and so whichever method you use, hopefully you wound up with with this answer. The noble gas we would use before calcium is argon. Okay, that's element number 18 over here. So that's got 18 out of our 20 electrons. So if we continued from argon, we'd only have 4s2 after that. So you can see that the noble gas abbreviation is much abbreviated, which is very useful. Okay, we've condensed all 20 of these electrons, all 20 over here, and condensed it by putting AR in square brackets. And again, if you want to fill out your 20 electrons using arrows to make an orbital diagram, all of these orbitals are going to be full, so you just put all 20 arrows into these orbitals. All right, here's another example if you want to take a crack at this one. So try to find selenium in your periodic table. Okay, that's element Se. Right. Find it in your periodic table and go ahead and write out its electronic configuration. Okay, so pause this video if you need some more think time, and here's the answer. Okay, so when you're done, if you want to check your work, selenium is element number 34. So if you want to check to make sure you did this correctly, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 4 adds up to 34. And you'll notice that selenium is in the fourth row and in the p block, and it's the fourth element of the p block. Okay. The interesting thing with selenium now is actually, if you're using your periodic table method of writing this out, please note that when you go through your d block, you have to drop a number for that d orbital. So instead of 4d, it's actually 3d10. Okay, so please note that. That's a common mistake a lot of students make who are using that periodic table method of remembering the Aufbau principle. Okay, so watch out for that. That's 3d10, not 4d10. Okay, so generally speaking, the other useful thing of the periodic table, besides using it as a tool for writing out electronic configurations, is knowing the patterns that we see in our periodic table. Because the periodic table is organized in such a way that we can see these patterns, that things are organized by their chemical properties, we can compare elements to each other and basically take advantage of knowing these patterns beforehand. Okay, so these patterns are called periodic trends, and I'm going to walk through most of these. There is one more periodic trend called electronegativity that we're going to describe in more detail in a later chapter, because that'll help us understand things like covalent bonding and intermolecular forces. So we'll leave that lesson for a later day, but for now I'll talk about most of the other periodic trends that we can pick out from our periodic table. Okay. So the first of these is what are called valence electrons. When I wrote out the noble gas notation of our electronic configurations, of our orbital diagrams, or when writing out our electronic configurations, I hid what were called the core electrons, right? We used a noble gas to represent those core electrons. The reason we did that is because those core electrons are kind of shielded in the middle of the atom, and they don't really do anything. They don't exactly get involved with other atoms because they are kind of in the middle of the atom, and other atoms can't really touch them. They can't access them. It's the outermost electrons, or valence electrons, that are the most important ones. And this is why noble gas notation writes out those outermost electrons. Right? After the previous noble gas, we pay attention to the remaining electrons, because those are the ones your atom's going to use for bonding. Okay, so these valence electrons match up with the group that your element's in. All right, so for example, you'll notice that all of the group 1 elements will end with something S1. Okay, so I'll show you some examples with a couple of alkali metals, and you'll notice that all of them end with something S1. Likewise, all the group 2 elements end with something S2. All right, and notice that those electrons correspond to their group numbers. The halogens are in group 17 or group 7a, and the reason for this is that they have 5 of those S and P electrons. Okay, they end with something S2, something P5, and in 2 plus 5, it matches that group number of 7, okay, or 7a rather. Okay, so it might be a little tougher to match up with if you're using the new numbering, because it might be labeled group 17 on your periodic table, but just realize it's got 7 valence electrons, even though it's group 17. Okay. So here's an example so you can see what I'm talking about. So if we look at lithium, which has 3 electrons and the configuration 1s2, 2s1, and we compare it to sodium, which has 11 electrons and has the configuration 1s2, 2s2, 2p6, 3s1, okay, those outermost valence electrons, so in the case of lithium, it's in that second shell, 2s1. In the case of sodium, it's that third shell, 3s1. In both cases, you have your electronic configuration ending with something S1. Okay, so those electrons will, that tells us that both of these alkali metals have 1 valence electron, and that is why they're both in group 1. Okay, and they're both going to have similar chemical properties because of this fact. Okay, so it's actually, you could think of, thinking about it backwards is probably the better way to think of it, that it's because of this configuration that they have those similar chemical properties, and that's why Mendeleev put them in the same group when he was organizing the periodic table for the first time. Okay. So the other patterns that we see in our periodic table have to do with trends that we notice as we go across a period or down a group. Okay, and you can combine these effects to go diagonally across the table too, of course. The 3 properties we're going to look at here are going to be atomic size or atomic radius. We're going to look at ionization energy, okay, how much energy it costs to remove an electron. And the third one is that electronegativity I talked about, which again we'll leave for a later chapter. So we'll focus just on atomic radius and on ionization energy for this chapter. So by atomic radius, or atomic size, we're looking at how atoms get bigger or smaller as we move around our periodic table. So if we are going from top to bottom on our periodic table, how do atoms change in size? Well, as you're adding more and more shells of electrons, atoms get bigger and bigger. Okay, so you start off with a small atom and the nucleus in the middle. Okay, if you have a shell of electrons, as you add more and more shells, those atoms are going to get bigger and bigger. They don't look perfectly like this. This is just like a cartoon of what an atom looks like. But the general idea is that as you add more and more shells, those outermost electrons are getting further and further away from the nucleus and making your atom bigger. Okay, it's giving it a bigger radius from the nucleus. All right. Now, what happens when you go from left to right in your periodic table? Okay, this is a little counterintuitive. This gets a lot of students because most students think that, well, as you're going from left to right, atoms get heavier. They're adding more protons and neutrons. They're getting heavier, and heavier things are bigger, right? Shouldn't our atoms get bigger as they go from left to right? This is the counterintuitive things. Atoms actually get smaller as you go from left to right. Now, why is that? It turns out that adding extra protons and neutrons doesn't really, while it changes your mass, remember, those protons and neutrons are crammed into your nucleus. They don't affect the size of the atoms. What affects the size of your atoms are your electrons, right? And if you're going from left to right in your periodic table, if you're going across a period, you've got the same number of shells. You're not changing the number of shells. Okay, so unlike going from top to bottom in your periodic table, instead of adding more and more layers, you're keeping the same number of layers, right? But as I pointed out earlier, you are increasing the number of protons. Now, while protons don't affect their size doesn't affect the size of the atom, you have to remember that protons are positively charged, right? You've got that positively charged nucleus in the middle of your atom. What's it doing to all these negative electrons surrounding it? Well, as you add more and more protons, you're increasing the pull on those outermost shells of electrons, right? So as you go from left to right in your periodic table and you're adding more and more protons, your atoms get smaller because that nucleus is pulling harder on those shells of electrons. Okay, so generally speaking, your atomic radius or atomic size decreases as you go from left to right on your periodic table. Okay, so generally speaking, I think I've gotten the size here. Atoms get bigger going down your periodic table as you add shells, and they get smaller going from left to right across your periodic table. So general trend, if you want to remember this when you're comparing elements, the general trend is atoms get bigger going down and to the left on your periodic table. So helium over on the top right is the smallest atom. Francium, which is not shown on this diagram, down here on the bottom left, is the largest atom that you have in your periodic table. But you can see, generally speaking, atoms are getting bigger as you move down and to the left. Okay, so anytime you compare two elements, just see where they are in relationship to each other. Okay, whichever element is more to the left or lower, it's going to be the bigger of the two atoms. Okay, a quick note here before I move on to ionization energy. We're going to talk about forming ions in more detail in later chapters when we talk about ionic bonding. But for now, realize that you can turn an atom into a positive ion by removing an electron from it. Okay, because electrons are negatively charged. If you remove an electron, you have an imbalance because you still have the same number of protons, but you're missing a negative electron. So the resulting ion is positively charged, right? What does that do to the size of your atom? Well, the remaining electrons get pulled in a little bit tighter because you have fewer electrons sort of repelling each other or shielding electrons from the nucleus. So whatever electrons you have remaining get pulled in tighter to the nucleus. So a positive ion is, generally speaking, always smaller than the atom it comes from. Okay, and by the way, we see the opposite effect with a negative ion. If we were to throw on an extra electron, because of the increased amount of shielding and repulsion between electrons, and without changing the number of protons, the atom generally your negative ion tends to be bigger than the atom it comes from. Okay, so something to keep in mind if you're comparing the size of an ion with the atom it comes from. Okay, let's talk a little bit about ionization energy and the trend therein. Ionization energy is the energy required to pluck away an electron to turn an atom into a positive ion. Now, this is always a cost in energy. It always costs energy to remove an electron from an atom. However, how much energy this costs varies from atom to atom. In the case of the alkali metals, which have only one valence electron, the relative cost in energy is pretty low. It costs very little energy to pluck away that outermost electron from the from the influence of its nucleus. Okay. Likewise, from your noble gases, generally speaking, it costs a lot of energy to pluck away electrons. That's why they don't like bonding with things. They want to keep all their electrons. All right. So what is that trend that we see there? Okay, ionization energy generally increases as your atoms get smaller, and it decreases as the atoms get bigger. Okay, so it's kind of the opposite of the trend we saw for atomic radius. So remember, atoms get bigger moving to the bottom left of your periodic table. Well, ionization energy increases as you go to the top right of your periodic table. Okay, and if you think about it, it kind of makes sense, right? If your atom is really small, that outermost electron is really close to the nucleus. It's really being held pretty tightly to that nucleus, it's going to cost a lot of energy to rip that electron away. But if there's a large distance between that nucleus and the electron, all right, there's a lot of shielding, there's lots of layers of electrons in between that are shielding that electron from the nucleus, then it doesn't cost as much energy to pull that electron away. Okay, so generally speaking, that's why there's the opposite trend in ionization energy. Okay, so the smaller the atom, the larger the ionization energy, the more difficult it is to remove an electron. With the larger an atom, the lower the ionization energy, the more easy it is to pluck away that electron. Okay, it costs less energy to do that. So here's a little study check, just make sure we've got that. So take a second, have a look at these, and see if you can figure this out. All right, and so feel free to pause the video, but if you've already taken a crack at this, let's go through the answers. So going down group 6A, or 16 if you've got a newer periodic table, the ionization energy increases or decreases. So remember, as you go down a group, your atoms are getting bigger, which means that ionization energy, which has the opposite trend, is decreasing. Okay? Likewise, with the if you're going from left to right in period 3, your atoms are getting smaller. Because remember, atoms get bigger going to the left of your periodic table and down, but since we're going to the right, the atoms are getting, smaller. And regarding metallic character, in case you're wondering about this one, remember, metals are in the bottom left of your periodic table. Nonmetals are to the top right of that sort of border. So generally speaking, bigger atoms tend to be more metallic. Okay, and smaller atoms tend to be more non-metallic. Okay, so generally speaking, if you're going down a group, you're getting into bigger atoms, and so therefore your atom's its metallic character increases. Okay, let's try an actual example of comparing individual elements. So look up carbon, nitrogen, and silicon in your periodic table. So if you don't have one in front of you, okay, if I were to draw, these are, these elements are all kind of right next to each other. So if you were to look those elements up, it would look kind of like this. So here are those three elements. Okay, so carbon's over here, nitrogen's over here, silicon's over here. Okay, here's phosphorus, oxygen, sulfur, and all those others, right? So yeah, so if you're looking for this is group 14 and 15 of your periodic table near the top. Okay, so with that in mind, comparing where they are relative to each other, which of these is the largest atom? Now remember, atoms generally get bigger. Oh, and by the way, feel free to pause here if you want to take some time to think about this. But generally speaking, atoms get bigger as you move to the bottom left of your periodic table. So the biggest of these three atoms would be silicon, because it's the bottom leftmost of these. Okay, which has the highest ionization energy. So remember, ionization energy has the opposite trend. Smaller atoms have higher ionization energies. And remember, atoms get smaller going to the top right. So in this case, it would be nitrogen. And which one belongs to group 15 or 5A? The only one for that is nitrogen. Carbon and silicon are in group 14. Okay. All right. So like I said, based on these patterns, you can figure out, when you're comparing two individual elements, or in this case, three of them, by looking at where they are in relationship to each other in your periodic table, you can sort of compare which one's going to be bigger, which one's going to have a higher ionization energy, and so on. Okay. But a question I often get at this point is, which of those changes is bigger? When you're going down, let's say you had two elements which were right next to each other. Okay, so let me give you an example here using those same four elements, or same three elements, but let's add a fourth one here. So let's say we had carbon, silicon, nitrogen, and phosphorus. Okay, so generally speaking, we compared silicon and nitrogen, and we knew that silicon is going to be bigger and nitrogen is going to be bigger, right? Going to be smaller. We could compare things within the same group as well. So I could tell you that silicon is going to be bigger than carbon, phosphorus is going to be bigger than nitrogen. Okay, I know that comparing things within a a period, we know which one's going to be bigger. The atoms get bigger as you move to the left of your periodic table. So carbon's bigger than nitrogen, silicon's bigger than phosphorus. I guess the question that pops up here that students often ask is, if I were comparing carbon and phosphorus, how do I know which one's going to be bigger? I know that carbon's going to be bigger than nitrogen, and phosphorus is going to be bigger than nitrogen, but is phosphorus bigger than carbon or vice versa? So to answer that question that often pops up, generally speaking, the changes going down your periodic table, down a given group, those gaps are larger. You see a bigger change than if you're going within a period. So to answer your question, phosphorus is much bigger than nitrogen. Carbon is only slightly bigger than nitrogen, so phosphorus is going to be bigger than carbon. Okay, but that being said, don't panic. You're not going to get asked a question like that. They wouldn't ask you to compare two elements that are diagonal in that direction. They would ask you to compare something like silicon and nitrogen, where it's kind of obvious that silicon's bigger, but you're probably not going to get a comparison of carbon and phosphorus. Okay? All right, but in case you were curious, that's how that would work. So that's it for this chapter. If you have any questions, let me know. Be sure to try the suggested practice problems. Unlike the last couple of chapters, I didn't feel like there was a very good selection of problems at the end of the chapter, so I recommend doing the example problems in each section of the material in the chapter. So when you're going through each of those sections, go through the example problems for practice. Okay? Okay, and yeah, thanks for watching, and I'll see you in the next chapter.